Good morning and welcome to the Mega Live Transformer Testing Seminar. This seminar has been broken down into 6 presentations from 6 different experts from mega sites around the world. There will be time for questions after every individual session, as well as a panel discussion at the end of the seminar with all of the speakers. If you do have any questions, please feel free to put them in the questions tab on the control panel on the right-hand side of your screen. We will have a 30-minute break for lunch at 12 o'clock and begin the next presentation at 12:30. I will now hand over to Tony Wills, our first presenter of the day.
Thanks, Steve. Yes, welcome to this Transformer Testing Seminar. The first presentation is a general introduction to Transformer testing, and in particular, a look at some test methods to detect mechanical changes in the transformer. So we'll look at when we might perform different transformer tests, the different types of tests that we can perform on a transformer, in particular diagnostic measurements and those that can identify mechanical changes inside a transformer, because we don't want to open up a transformer to see what's going on. We want to make as many measurements as possible from the terminals and try and work out the state of the equipment inside the transformer. So for that, we'll particularly look at frequency response analysis, short circuit impedance, and frequency response of stray losses. So transformers can be tested throughout their life. A lot of tests can be performed during factory acceptance testing. This is a nice clean environment normally, where it's easy to make a lot of tests. In a factory, you can have a lot of test equipment available to perform all of the required measurements. And it's also a good chance to perform some reference measurements, so that when we are making further tests in the future, we can compare with those tests. Some of those may be added to the nameplate of the transformer, so that's always a good way of identifying the condition of the transformer and how it's changed from when it was brand new. Most transformers will undergo routine tests, maybe at a certain time interval throughout their life, where more information can be gathered about the condition of the transformer. These may be condition-based tests. So yeah, as transformers get older, they're more likely to fail, and maybe we need to do more testing to identify their condition so that we can carry out some maintenance before they fail, or yeah, ultimately replace the transformer, ideally before it fails. We may also perform extra measurements after faults have occurred on our system. So if we have maybe short circuit faults, very high currents flowing, cause huge stresses inside the transformer, can cause it to change. Or maybe lightning strikes can cause insulation damage, then yeah, it's always a good idea to perform extra measurements just to be confident that the transformer is still in good conditions. If it goes back into service, it will perform properly for the next period in its life. Ultimately, we'll need to perform some tests to define when the end of the life is and when it needs to be replaced. So yeah, those are important measurements as well, and perhaps even post-mortem tests if a transformer has failed, to try and identify what has happened. So there are many different tests that we can perform on a transformer. Not one test will tell us everything we need to know. And so that is why there is a wide range of different tests. Many of the tests are based around identifying the condition of the insulation of the transformer. A lot of insulation tests in any high voltage equipment give us a good indication of the overall condition of the equipment. As equipment ages, dirt and moisture deteriorate the insulation, and so it's a good way of identifying overall condition. So yeah, we can measure insulation of a transformer both with a DC test voltage and an AC test voltage, and measure the tan delta or power factor of the transformer. We can expand this a bit more over a variable frequency using frequency domain spectroscopy, and that helps us to identify the condition of both types of insulation in a two-part insulation transformer, both the oil and the paper insulation. We can perform oil tests, which is sometimes very convenient. We can take a sample of oil, measure the breakdown strength or the water content or the tan delta. So that's a nice quick way of looking at the insulation condition sometimes. We can measure partial discharges, which are particularly good at identifying voids in insulation using various different techniques. And we can look at the dissolved gas analysis to maybe identify the condition of the transformer and also give us an idea of what further tests we should perform to really identify what is happening inside the transformer. We can also measure a few different parameters of the winding itself in the transformer. So both the winding ratio and the resistance can be measured. We can measure the magnetizing current, can help to identify short circuits in the winding. And most transformers will have a tap changer, which is a mechanical device, so more prone to failure. So it's always good to make a few measurements on the tap changer. The final section of transformer tests are based more around the mechanical state of the transformer, whether anything has moved inside the transformer due to transportation, lightning strikes, high fault currents. They can all cause mechanical changes in the transformer, which could lead to failure. So frequency response analysis, impedance or leakage reactance measurements, and frequency response of stray losses all can help to identify any mechanical changes. There's a useful document, a technical brochure from Seagray, which talks through a lot of these tests, and there's this useful chart in there which shows us for each of the different diagnostic techniques what type of problem can be identified. So you can see from this, no one single test can find all sorts of problems in a transformer, and each type of problem may be identified by several tests. So it's always a balance between knowing what tests will identify a problem and what test equipment is available. So an insulation test on a transformer can be a quick check that the insulation is good between windings, or for the core to earth as well, or for the windings to ground, to the tank of the transformer. Because a standard insulation test is a DC test, it's not suitable really for all types of insulation. Bushings, because of the graded insulation, really don't respond in the same way to a DC test voltage as they would to an AC test voltage. So a tan delta test is more suitable for them. But for an insulation test, we can use the guard terminal, which can help identify the location of poor insulation. So as you can see from the picture here, inside a 2-winding transformer, we really have 3 parts of insulation between the high voltage winding and the low voltage winding, between the high voltage winding and ground, and between the low voltage winding and ground. And so if we use a guard terminal, we can identify different parts of the insulation by guarding out the parts that we're not interested in. So an insulation test is typically carried out at 5 or 10 kV, so maybe not at the rated voltage of the transformer. We're really only trying to look at the condition of the insulation with the test voltage. We're not overstressing it, which could cause unnecessary breakdowns and deterioration of the insulation. So for transformers and bushings in particular, a tan delta or power factor test is a good test to perform. So this is an AC insulation test where we are looking at the resistive current and the capacitive current from the AC test voltage that's applied. Typically, a test set may be 10 or 12 kV, so it may be stressing the insulation more than a 5 kV DC test. And by measuring the tan delta, the angle between the or 90 degrees from the applied voltage and the actual measured current, that's showing us the amount of losses in the insulation. Very similar to power factor for all good insulation. So tan delta is the resistive current divided by the capacitive current. Power factor is the resistive current divided by the total current. But for good insulation, the total current and the capacitive current are very similar. And by measuring the tan delta, we may be able to compare with values on the nameplate from when the equipment was manufactured. It's a very good test for trending. We can identify deterioration in the insulation. We also measure the capacitance value, which is really a fixed value in insulation. It's just the dielectric between the two conductors of the part that we're measuring, and it should be very stable through the life of the equipment. So we can both measure the tan delta value, which gives us an idea of the condition of the insulation, and any more than 1% of tan delta is identifying that the insulation is deteriorated. But we're also measuring the capacitance, and any change in capacitance value of over 5% is also a cause for concern. So frequency domain spectroscopy or dielectric frequency response takes tan delta measurement one step further and measures tan delta over a frequency range of typically maybe 1 millihertz to 1 kilohertz. So this can be done at a lower voltage because really tan delta shouldn't be affected too much by voltage if there's no partial discharge present. And by measuring over this frequency range and comparing it to the modeled equivalent circuit of the transformer, of a 2 insulation system transformer, if it's oil and paper, we can quite separately identify the condition of the oil and the condition of the paper insulation. And we know that moisture migrates from the oil insulation into the paper, and the paper can store a lot of moisture compared with the oil, and it's a very good indication, the moisture content of the paper, of the age of the transformer. So from this test, which is performed typically at 140 volts and may take about half an hour because of the low frequencies that are involved, but by modeling the insulation characteristic over these frequencies, we can measure the tan delta value at 50 hertz, as well as a temperature corrected value at 20 degrees C. And then we can also measure the moisture content of the paper insulation and the power factor or conductivity of the liquid insulation, the oil as well. And a very simple traffic light system to identify the condition of all of these parameters can be shown in the results. So it's a very quick and easy method of identifying the age of the transformer. So taking an oil sample is often a very common way of identifying insulation condition of a transformer. Oil acts as an insulator and a coolant and is circulating around the transformer, so it's kind of absorbing moisture from the air and transferring moisture into the paper insulation. As the oil degrades, it can be oxidized and sludge can be formed. So an oil sample can give us a lot of information. The basic test for oil insulation is an electric strength test, often to the European norm 60156. And it's a good, quick indication of the water content and any particle content in the oil. Typically, the test voltage is increased to about 60 kV, and we measure the breakdown value a few times and look at the average value to get a good overall idea of the condition of the oil. We can also perform a separate test on oil insulation, a water in oil test to actually measure the water content, often with a Carl Fisher titration technique. And this can give us a parts per million value of the water content. So this can indicate whether the transformer is absorbing moisture from the air, which is deteriorating firstly the oil and then the paper insulation. We can also perform a tan delta measurement, more of a laboratory measurement, but this is an early indication of acidity in the oil, which obviously will start to break down the paper insulation. So that's another AC measurement of the insulation quality. And we can also measure oil resistivity, a DC measurement, which is good to identify the state of oil when it's being reclaimed. And as I mentioned earlier, dissolved gas analysis is a good way of identifying what kind of fault is occurring in the insulation and may point us towards what other electrical measurements we carry out to really identify what is happening in the transformer. So partial discharge measurements can be performed throughout the life of a transformer. During factory acceptance testing, an absolute level of discharge can be performed in a controlled environment. But during the life of the transformer, partial discharge measurements can also be performed. But yeah, in a noisy environment, it's not always as easy to make all of the measurements to the same level. So we can perform online and offline testing for on-site investigations, or we can perform online monitoring, continuous measurement of partial discharge, particularly using a bushing tap, capacitance tap for measurement, or we can measure with acoustic or UHF sensors to sometimes pinpoint the location of partial discharge within the transformer. So that can be performed continuously for critical transformers so that we can get a very quick indication of when partial discharge levels increase. And so that can warn us immediately that there's a problem. So a turns ratio test is a very basic test on a transformer. It's often performed in the factory and easily performed on site as well. It's an AC measurement by measuring the voltage that's applied to the high voltage winding and the voltage that comes out of the low voltage winding. We can measure the ratio of the transformer. So it's a very simple test to perform, but it's often much more convenient and safe to use dedicated test equipment to do this. This uses a lower test voltage and all the results are documented. So particularly when we're testing a transformer with a lot of taps, we maybe have 20 or so taps, 3 phases, we can soon generate a lot of information and not only measure the ratio, we can also measure the test current or magnetizing current and the phase deviation between the high voltage and low voltage windings, which can all help us to identify problems that are occurring inside the transformer. Winding resistance measurement is another very common test to perform on a transformer. So often a full terminal measurement so that we can accurately measure low values of resistance using separate current and voltage measurements. And so typically we would inject a current of a few percent of the rated current of the winding and measure the resistance. And so it's very common to use it in a factory test, really, to measure the temperature inside the transformer, knowing how the resistance of the winding varies with temperature. So that's a heat run test, but we can also use winding resistance as a diagnostic tool in the field to detect any bad connections inside the transformer from one terminal to another, so from bushings to windings, or also basic tests of tap changer, particularly the tap changer connections and contacts. So unlike a ratio test, we don't really know a lot of the time what the actual factory measurements of the winding resistance are. Like I mentioned, they vary with temperature. So often this is a comparative test, and the results on the screen show us a poor measurements of winding resistance where there's obviously some problem on the blue phase, and higher resistances are measured compared with the red and the black phases there. So it's a nice way to indicate when there is a problem by plotting the characteristic like this as the tap is changed and we measure the winding resistance at each tap position. So magnetizing current is a useful parameter to measure to identify particularly any shorted turns inside the transformer. And as I mentioned, it's often performed during a ratio test at quite a low voltage. So in this example, the test voltage I think was 250 volts. But it can be performed at a wide range of voltages, but obviously any comparisons need to be performed at the same voltage. But again, often the comparisons are between 3 phases on the same transformer. Typically the center phase is better coupled, so we'd have a lower value of magnetizing current on the center phase. You may be able to see here the magnetizing current on the first and last phases was 40 or 50 milliamps, and on the middle phase it was around 30 milliamps. So you can quickly identify any problems with magnetizing current during a ratio measurement. Sometimes we can use a higher voltage from a tan delta test set to perform magnetizing current up to rated voltage of the winding. A magnetic balance test can be used to identify this magnetic state of the core, particularly after a winding resistance measurement, which is a DC high current test. We can magnetize the core of the transformer. So before we perform other tests and measurements, or before the transformer goes back into service, it's a good idea to demagnetize the transformer. Per will talk about this in detail in a moment. But a magnetic balance test is a quick test that can identify whether the transformer is demagnetized or not by applying a known AC voltage to each phase in turn and checking the distribution of the induced voltage on the other phases, we can see if the transformer core is magnetized. So typically we may have some results as shown on the graph on the screen, where you can see when we apply the voltage on the red phase, the voltage distributes fairly more on the middle phase and less on the end phase. And if we apply on the yellow phase, it should be a very equal distribution for a demagnetized core. So that's 3 separate measurements, measuring by applying the voltage to all 3 phases and measuring the voltage on all 3 phases at once. Another useful test to perform is on-load tap changer measurements. While an on-load tap changer operates, there's a number of different switch positions that are used through transition resistors to get from one tap position to another without there being an open circuit. And if we dynamically measure the resistance during this process, we can measure the operating times of the switch and also the values of the transition resistors. So again, we're getting a lot of information about what is going on inside the transformer without actually having to open up and see what is going on just by measurements from the terminals of the transformer. So Ola will talk more about this later this morning. So now moving to more detail and looking at some of the tests that can help us identify the mechanical state of the transformer. A sweep frequency response analysis is a simple test to perform that can identify a lot about the internal structure of the transformer. It's a fingerprint test, so we're always making comparisons, ideally with a measurement that has been made on the same transformer previously. So it's an offline test after transportation or a fault has occurred in the transformer, which could have caused mechanical changes to the winding or the core in the transformer. And it's a test that measures the impedance between terminals, and because a transformer is a complex series of resistance, inductance and capacitance, and we measure the admittance over a wide frequency range from a few hertz to a few megahertz, any changes in different parts of the transformer can be detected, and they're plotted on a curve. And so if we see any variation at a particular frequency, that is identifying some change has occurred inside the transformer. So this test can detect a number of problems with core of the transformer or winding problems or other electrical faults in one test. So here's an example of 2 different measurements taken at different times. The red trace and the blue trace, you can see there's obviously a difference in the lower frequency response. And the different frequencies identify different parts of the transformer. So the lower frequencies, the larger components in the transformer, the core or the windings. The middle frequencies are changes in the windings, and higher frequencies, the smaller components in the transformer, the taps or other connections. So we can start to identify what is happening in the transformer from measuring over this frequency range and plotting the ratio of the input voltage, typically 10 volts, against the frequency from a few hertz to a few megahertz. So we can detect a number of faults like those shown in the pictures here. We can identify lots of physical changes, mechanical changes within the transformer. So any movement of the core or the windings, and even faulty core grounds and open circuits and short circuits can also be identified. We make a number of measurements, typically on a transformer. And usually the results are best when they are time-based comparative tests, so on the same transformer. So ideally we have some reference measurement that is made either at the factory or maybe during commissioning. And then later in the life of the transformer, particularly after transportation or if there's a fault, we can repeat the test and compare the two traces for a number of different measurements. Obviously, we haven't always got a reference measurement from that transformer, so we may be able to compare with a transformer of the same type. We may have a number of transformers all of the same specification on our system, so we can maybe compare two similar transformers. Or failing that, we can also do some comparisons between phases. We're lucky that all this equipment is a three-phase equipment, so that we can always compare between phases. Often the end two phases have very similar response, so we can do some comparisons even without any previous measurements. The measurement philosophy for a frequency response analysis is very simple. If we have a new measurement that's the same as the reference measurement, then we're quite happy that the transformer is in the same condition that it was before, and we can put it back in service. If we have a different measurement, then we maybe need to use some of the other test techniques that we've looked at previously, make some further diagnostics and try and work out what is happening. So the test setup is typically like this. The test voltage is applied from the tester to one terminal of the transformer, and another cable measures how much of that test voltage actually reaches the terminal of the transformer. And then the black lead shows us the measurement connection. So this is how we compare the voltage that's applied on one terminal and the voltage that is shown on another terminal, and we look at the ratio of those two. The tester can be battery powered and small. It's only a very low power device, so we can use a Bluetooth connection to a laptop that is controlling the tester and showing us the results. Typically we make a number of measurements on the transformer while we are there, so we can perform measurements between pairs of HV terminals and between pairs of LV terminals, and ideally with the tap changer in the maximum and the minimum positions. And then it's also useful to measure between high voltage terminals with a short circuit on the low voltage windings as well. So that gives us about 12 tests for a 2-winding transformer, and each of the tests takes about 90 seconds to make the measurements over the frequency range that's suitable. So this shows us how a test is performed. So the trace is quickly built up from measurements that are made by outputting the voltage onto one terminal and measuring the voltage that is on the other terminal that's being measured. So we can see in the top left of the screen, we have those maybe 12 tests that we are going to perform on this transformer. And in just over a minute, we will create a trace like this from a few hertz up to, I think it's 2 megahertz in this example. So on its own, the trace doesn't really mean a lot, but if we have some previous measurements, we can compare with a historical measurement that we've got from a factory acceptance test or a reference measurement that we've made. So there's one test completed. And now, yeah, we'll do another test. I think the only thing that changes here is the tap has changed slightly, so that will change the impedance of the high voltage winding. This is a high voltage winding measurement. So now we can repeat the test at a different tap, and you may just be able to see there's another trace that is being drawn on the chart in a sort of greenish color, but it's a very similar one to the first trace. Apart from at the lower frequencies, there is a small difference because the impedance of the winding has changed a bit because of the different tap position. But yeah, hopefully you can see there the trace is followed in a very similar way over all the middle range frequencies. And now the test is being performed up in the megahertz range. And because, yeah, the tap has changed, there are some differences at the higher frequency response. So yeah, we can see there is definitely some minor changes in between the two measurements. So that's how we can identify physical changes inside the transformer. Here's an example of two tests that are performed at different times. Yeah, it looks a bit blurred. It's not your eyesight. There are two traces that are very similar that are performed at different times. So we can see the low voltage response at the top and the high voltage winding response at the bottom. Very similar measurements. Even when we look in more detail at the resonant frequency there, we can see that the two traces are very similar. There are some changes at the high frequency end. This can be due to different tap positions like we saw earlier, or maybe due to the earthing that is performed during the measurement. The next test we look at is the leakage reactance or short circuit impedance test. This can help us identify any deformed winding, and it's measured by applying an AC current or voltage to each winding with the low voltage windings short circuited. So then we are able to measure any leakage from the high voltage winding to the low voltage winding, and we can compare often with a factory test or a measurement on the nameplate. And if there's more than a 2% change in the impedance, then that is cause for concern, and we may need to identify what is happening. So this shows us how the test is performed. We apply a voltage to each phase in turn with the low voltage windings short circuited. And then in this example, we apply a 1 amp test current to the first phase. And so we measured 232 ohms of impedance. And then we rotate the test connections, so we apply to the next phase, still with the low voltage winding short circuited. And again, we apply 1 amp of test current and measure the voltage, both the reactive and the resistive voltage, to calculate the impedance and the reactance. And finally, on the last phase, again, we change the connections from a single phase tester and repeat the test. And from those measurements, we can see the variation in the impedance from the nameplate value to the measured value today. So anything over 2% variation is showing us that there has been some mechanical changes in the winding. And the final test we'll look at is frequency response of stray losses, which can help us identify hotspots between different strands on an individual winding. And it's really a variable frequency leakage reactance test, so similar to the test we just looked at, but performed over a range of frequencies, and again measuring the AC resistance to identify stray losses. So again, it's nice to compare between a reference measurement that we've had previously, but we can also compare between phases. So if we see an inductance change of over 2.5% or a resistance change of over 15%, then that is cause for concern. So the test connections are the same as for the leakage reactance measurement, but now the test is performed probably at a lower current over a frequency range of typically 20 to 500 hertz. And then we build up a picture of how the leakage reactance varies on all 3 phases over that frequency range. And what we're looking for is a change in the characteristic from one phase to another or from previous measurements. So again, it's performed on all 3 phases. And typically we'll end up with some results like this, where we can plot the characteristic of the resistance measurements at different frequencies. And here we can see, there's 2 phases overlaid on the top and a 3rd phase with a lower resistance. So yeah, I think it's not really a problem with the leakage reactance. There's some extra resistance for the blue winding in this case. So that's the end of the presentation for the introduction to transformer testing. I don't know whether there's time for any questions now, Steve, or shall we continue?
Yeah, there's a few questions come in, Tony, if you wouldn't mind answering.
Okay.
So just on your FSRL results, we had a question from Sebastian that's come in saying, what is the percentage of error on the measurement if we didn't disconnect the cable? Because obviously disconnection of the cable can be a problem for some utilities where the time to stop the substation for maintenance is limited.
Yeah, I think it shouldn't really affect the measurement too much, just having a cable connected to the high voltage winding, because it's really the reactance of the transformer that we're measuring. So I think usually any cable connections shouldn't really interfere too much with the frequency response of stray losses measurement.
Okay, thank you, Tony. We have one more from Mohammed. When performing winding resistance test on a power transformer, I found one winding that is bigger than the other 2. The unbalance was 11%. Insulation resistance was okay. Tan delta test at 50 hertz is okay, and the ratio test is okay. So what could be the problem?
That could be an issue with some bad connection on that phase inside the transformer. So yeah, if it is 11% higher winding resistance than the other two phases, then that is a significant deviation. It might be interesting to perform the measurement at a number of different current levels and try and identify what is happening. But yeah, that is likely to be a poor connection. I think maybe check the tap changer if it's an external or internal tap changer. Just check that resistance or the operation in some way, because it's likely to be a connection problem and quite possibly in the tap changer.
Okay, thanks, Tony. We have a couple more, if that's okay. Is there enough power from a tan delta test to test the transformer?
Yeah, okay. Yeah, normally a transformer doesn't have too much capacitance, and so yeah, there is enough power. But if the test set doesn't have much power, we can maybe just use a lower voltage, and then the power will be less, because I said the test voltage for a tan delta measurement isn't often that critical for a transformer. It is for motors and generators, but not for transformers. We may be able to use a lower frequency for some testers as well, and that will reduce the power required for the capacitance measurement. Or ultimately, we can also use a resonating inductor sometimes, so then the power is supplied from the inductor as well as the test set, and so that can help us measure higher capacitance loads.
Thanks, Tony. Just one more that's come in. Is the order of tests important when performing several measurements?
Okay, yeah, that's a good point. Like I mentioned, if we are doing a winding resistance test, we need to demagnetize. I think Per is just about to talk about this, so maybe he will mention this as well. But if we demagnetize the transformer at the start of the test, then we know its condition. Whereas if we perform lots of tests, particularly frequency response analysis, then that is affected by the state of magnetization of the core. So our recommendation would be to perform a winding resistance measurement first, and then demagnetize the core, and then we're okay to go for all the other tests, because we know the state of magnetization of the core.
Thanks, Tony.
Okay, thank you.
Just one more that's literally just come in. Are these tests forms part of type tests?
Yeah, in a type test could involve all of the tests I've mentioned, and other tests as well. There can be many other tests that are performed as part of type testing. So yeah, what I'm looking at today is mainly tests that can be performed on site for routine maintenance for a transformer once it's installed. But yeah, for type testing, many other test types are available as well, but I haven't mentioned them all today. But what we're really looking at is more about measuring routine maintenance to identify the condition of a transformer that has been installed.
Okay, thanks, Tony. That concludes the questions for your session.
Thank you.
Okay, I will now hand over to Per, who will now begin his presentation.
Okay, let's see. I just need to find where to share my screen. This one. So, Steve, can you see this?
Yep, absolutely fine.
Absolutely fine. Perfect. So, well, welcome to this presentation on transformer demagnetization. And that last question was almost as if it was planted because, well, the order of in which you do the tests is quite important, and I'm going to touch upon that. So my name is Per Lindestam. Sorry, wrong. There. My name is Per Lindestam. I'm based in Sweden, and I'm the commercial product manager for, amongst others, the transformer testing products that we do in Sweden. And this presentation is going to cover multiple topics. We're going to speak a bit about general electromagnetism, more specifically about magnetism in the transformer, and then look at the residual, the causes and effects of the residual magnetization in the transformer, and then look at methods for demagnetization, and then finally, but not least, last but not least, a demonstration of how demagnetization is done in our substation transformer tester tracks. This presentation is going to be quite heavy on physics, but I'll try to keep it simple because it's hard to understand magnetization if you don't have the basic concepts. So, as you all may know, a current that flows in a conductor induces a magnetic field. This was discovered by Hans Christian Ørsted, the Danish physicist, in 1820 when he noticed that a compass needle moved when it was close to a conductor. This magnetic field is generally drawn as field lines, the blue lines in this picture, and the higher the density of these lines, the higher the field strength. All these field lines are closed loops. I've only drawn 2 closed loops here, but they go out basically into infinity and are closed. And the magnetic field strength created by this current is denoted H and is measured in amperes per meter. If you take this coil and you want to calculate sort of how does the magnetic field strength relate to the current, and that is quite easy. If you do a line integral, that you sum up all the tiny elements of the magnetic field strength over a loop, then you will get a value that is proportional to, or equal actually, to the current that is flowing through the conductor times the number of turns that you have in your coil. So H, the magnetic field strength, is thus proportional to the current that flows in a conductor. There's, however, a complication with this, and it's that it's only valid in vacuum. I'm a physicist, and physicists, we love vacuum because everything is more simple, but reality complicates things. So we have to introduce a new term, which is called flux density, and is denoted B. It's measured in Teslas or Webers per square meter, and it's basically a term to handle the magnetic properties of the real world. So here's one sort of the first of 2 quite tough theory slides. So the total magnetic field is equal to the free magnetic field and the bound magnetic field. And the free magnetic field is the H that was in vacuum, and the bound magnetic field is called M, and that is the magnetization of the material. There is also a scaling factor here, which is the permeability in vacuum, which is called μ0. For small magnetic field strengths, the magnetic field strength plus the magnetization could be said to be linear with the magnetic field strength by a factor μr, which is the relative permeability, and that is the permeability of a specific material. That is how good that material accepts a magnetic field. And as I said, or as you can sort of deduce from the previous equations, for vacuum, the μr is equal to 1. Then there are several different types of materials. You have diamagnetic materials, that is materials that basically deflect the material, reject the magnetic field, and the μr is smaller than 1. Copper, for instance, is one of these materials. Copper slightly resists the magnetic field. Superconductors are another good example. When they're superconducting, they basically reject almost the entire magnetic field, and that's why they can levitate on magnets when they're cold. Then you have paramagnetic materials where the relative permeability is larger than 1, and these are materials that slightly attract the magnetic field. Oxygen is one of these materials, for instance, and many other materials. Then you have a ferromagnetic material, which is interesting in the business that we are in, and there the relative permeability is much larger than 1. And this means that basically all the field lines, all the magnetic field will be guided inside that material. If you draw this equation, if you draw them in a diagram, you can see that you have B and H, B on the y-axis and H on the x-axis. And in vacuum, you have only the relative permeability of 1. So you have so it scales linearly with a factor of 1. The diamagnetic is slightly smaller, and the paramagnetic one is slightly larger. And then you have the ferromagnetic, which sort of they're affected very much by the H field. What happens with the ferromagnetic materials is that they reach saturation at a certain point. And that is basically due to that all the magnetic dipoles in the material, they are aligned with the magnetic fields, and from that point on, that material will act as vacuum, more or less. So with this knowledge, let's make a transformer. And then you need 2 coils. But if you were to put these in vacuum, only a minor portion of the magnetic field would travel from one coil to another, and you would have very poor efficiency of this. So you need another material to better guide the coil. And then knowing that you have, knowing the properties of a ferromagnetic material, you can actually make a core of a ferromagnetic material that guides the majority of the field lines from one coil to another coil, to the other coil. And as the magnetic field in both coils is proportional to the current flowing through the coil times N, you basically, and you have the same magnetic flux in both sections of the core, you could actually get the transformation equations that we are quite familiar with, where the current scales with the number of turns and also the voltage. To be able to relate we have related the magnetic field strength to the current, but we also have the voltage in the transformer. And to be able to relate the voltage to something that we have the magnetic properties of the core, we need to introduce another term, which is magnetic flux. And that is basically the surface integral of the normal component of the magnetic flux density passing through a certain surface. And since in the transformer the surface doesn't change, the surface of the core doesn't change, well, that is basically the magnetic flux flowing in the core. The magnetic flux is measured in Webers or volt seconds, and that means that if you can monitor or measure the voltage and time, then we can determine the flux density in the core. That is the factor B. So what happens in the transformer and how is it magnetized? If we plot the same curve that we had before with H on the x-axis and B on the y-axis, and H is proportional to the current and B is proportional to the voltage times the time. When you inject a current, first of all, you magnetize the core. This is valid for both DC as well as the positive cycle of an AC current. At a high enough current, you will reach the saturation point where all the ferromagnetic molecules are aligned with magnetic fields, and actually you lose the benefit of a ferromagnetic core. Normally, you don't operate a transformer up to this point. You stay well below it, perhaps 10% off to 90% of the saturation level. If you, again, remove the current, or if in an AC cycle it turns and you get the negative flank, then the magnetic flux decreases. But due to the magnetic properties of the core material, it follows a different path, and the core remains magnetized even at no current. And this is the M term in one of the equations we had before. And this remaining magnetization of the core is called remanence. Basically, you cross the y-axis, you still have a certain magnetization left in the core. If even more negative current is applied, that is, the AC cycle continues, or if you go down with a negative DC current, the magnetization occurs in the opposite direction until you reach saturation in the other end again. The remaining magnetization that we have had, the remanence, is cancelled out at a certain H, which could be said to be proportional to a negative current, and that is called the coercive force. And the work done to overcome this coercive force for each power cycle is actually one of the sources of loss in a transformer. If you go back up again with a positive current or a positive DC current, you will pass through both a remanence, a negative remanence point, and also a positive coercive force point until you reach saturation again. And this full curve, the loop, the full BH curve, is called a hysteresis loop. And that is basically one of the fundamental concepts of magnetization. Normally, a transformer is, as I said, operated below the saturation level because you lose the benefits of the ferromagnetic material at saturation, so you want to stay clear of those. So basically, you operate the transformer along a smaller loop that is inscribed in this larger saturation to saturation loop. This smaller loop also has remanence and coercive force points, of course. What are the normal causes then of core magnetization? The most obvious one is that you shut off the transformer at a random point in the power cycle. That could be anything. It's illustrated here with the red line. And basically, when you shut it off and the core is de-energized, you will end up with some remanence. That could be both negative or positive. In this case, it's written as positive. Another cause is that you, during winding resistance measurement, as Tony explained, you apply a DC current, which is actually meant to saturate the core. After you discharge the energy in the winding, you will then end up with a maximal magnetization of the core, basically. You will end up with a very large magnetization remanence. And that is the green curve in this diagram. You could also have geomagnetic phenomena similar to naturally occurring magnetism that could play tricks with your transformer, so that you could actually have spontaneous magnetization of the core. The effects of this remanence or residual magnetization. Well, the most obvious one is that when you want to, after your test, you want to put your transformer back into service. Since the core is magnetized, you will need less work to magnetize the core during the first few power cycles. And that could lead to a higher than normal inrush current, which both could damage the transformer, but it could also lead to protective relays tripping, believing that this is an adverse event. So you could actually, by not demagnetizing the core, you could actually create large power outages with huge costs associated. Another quite bad thing with residual magnetization is that you could get incorrect measurements. Excitation current, for instance, as Tony discussed, could be incorrect. You have you have some magnetization in the core, and you will need less work to magnetize the core. The sweep frequency response analysis curve could be totally incorrect. This is also something that Tony demonstrated, and the curves here is an example of what it looks like when you have a magnetized core. You have the top curve, the orange one is a magnetized core, and the demagnetized core is the green one. So you get sort of in the portion that describes the core and the winding, you could get incorrect results. And of course, if you do a magnetic balance test, if the core is magnetized, you won't get the correct results. So this is the reason actually why demagnetization is included in most testing standards. All these are IEEE standards, American versions. This is a webinar aimed at Europe, but also in the SIGRE testing guides that Tony mentioned, there is recommendation to demagnetize the core before doing other tests. So the mega recommendation is actually to always demagnetize your transformer before doing other tests, and also to pay attention to in which order you do the measurements. You always start with winding resistance measurement, and then you do the demagnetization to make sure that you don't have any magnetization left in your core. And these are the instruments currently sold by Mega that can help you demagnetize the core. All these instruments have the capability of doing winding resistance measurements. And since winding resistance measurement is one of the tests sort of creating this problem, we also feel that it should be included a demagnetization method. Starting from the left, we have TRAX, which is our multifunctional transformer and substation tester. This has the most advanced demagnetization method. It's automatic and it's fully adapts to the properties of the transformer. The middle three ones, the MWA 300, the MTO 300, and the MTO 210 and 250, also have automatic demagnetization, but they use another passive method which doesn't doesn't use feedback from the transformer in the method. And last but not least, we have the MTO 106, which is our entry-level winding resistance analyzer. It has a manual passive method where you actually have to go and switch the cables, but we have a method described to demagnetize the transformer for that, even for that basic unit. There are some, I touched a bit on the different methods for demagnetization of the core, and there are some different methods. I'm going to go through three of them. And the best method is actually to use a AC voltage with an amplitude going from saturation to saturation point, and then decreasing that level down, the amplitude down to 0. This is ideally done to the middle leg of the transformer. All the demagnetization methods use the middle leg because then it spreads to the other two legs. And basically what you do is that you go through smaller and smaller loops until you reach the center of the diagram. This is for power transformers very unpractical, especially in the field, since you need to go to line voltage. It's expensive and it's highly dangerous. So this is not something you can do in the field. You maybe can do it in the factory if you've done tests, but even then it's very dangerous. For other types of transformers, current transformers, for instance, you can do this quite easily. And in the TRAX, we actually use this method to demagnetize the current transformers after the winding resistance test that can also be done to current transformers. So we need a better method to test to demagnetize the transformer. And in the testing standards, a method is described where you use DC current of alternating polarity and decreasing amplitude, starting with the saturation current. And you discharge the winding between the steps. That is, you allow the energy stored in the transformer to dissipate. So this method is used in the MTO and MTO range of instruments, and also the AMWA from Mega, automatically for the larger ones, and passively manually for the MTO 106. So basically you have a current of 100% positive to the positive saturation point, and then you go negative, you discharge the winding, you go to negative 100%, discharge again, you go to positive 20%, discharge, and so on until you, until you're at only 1% of the current needed for saturation. You generally get very good results with this, but it's time consuming, and you also can have some remnants left in the end. And that is because you don't adapt to the real world situation of the transformer. The method that is used in the tracks is an adaptive method. And what we do is that we measure the voltage and the time during the injection of current, and also during discharge. And since we knew that the B factor, the magnetic flux, since we knew that that was proportional to the voltage times time, we can use the measured information of voltage and time to calculate the remnants and also the center point in this magnetization diagram. So basically what we do is we inject a DC current to saturate the core. We measure this continuously so we can see that we saturate the core. And then straight after we discharge. And during both these events, we measure the volt seconds put into the transformer. That is the voltage applied and the time it needs, and the time that that voltage is applied. Then we inject a negative current until we reach the same number of volt seconds as we did in the positive direction. And we discharge again while measuring the volt seconds. Then we decrease the polarity, we inject positive polarity current again, but only with 50% of the volt seconds in the previous cycles, and we discharge again. And then we repeat this a few times in ever decreasing steps. With this method, since you get feedback from the transformer where you are in the magnetization diagram, we can achieve a lower remnants and also a much, much faster demagnetization. And these are some test results made on the two transformers that we have in the Sweden sites. We've first done it with a smaller distribution transformer, a 500 kVA transformer. And the remnants before the winding resistance measurement was approximately 50%, 52 to 53%. After the demagnetization, we achieved 1% remnants with the tracks. It's actually harder to measure exactly at those low levels, and around 10% with the MTOs. And we needed 15 seconds with the tracks since it's fully automatic and time optimized. We needed 90 seconds with the MTO 2010, and that is due to that we don't use any feedback from the transformer, and 180 seconds with the MTO 106, and that's because it's fully manual. You need to switch the leads. We also did the same tests on a larger transformer, a 20 MVA transformer, and we started with a much lower remnants, about 12%, and got to about 1% with the tracks and about 5% with the other instruments. And it's actually with these larger transformers where you benefit most from the tracks. The demagnetization took only 42 seconds with the tracks and 6 to 8 minutes with the MTO instruments. So now we're going to have a look at how this is done in the tracks. This is, to start this is a recorded video, so if I lose track, please forgive me. So this is what the main interface looks like in Tracks. Tracks is our, it's our transformer and substation system. It's a multifunctional test system. It uses all test instruments are named apps. So basically you have one app for each test instrument. You can also, of course, make new tests or load old tests. And if you go into the app screen, you get the apps are sorted in the depending on which test object you want to test. So this is the power transformer tab. You also have the current transformer tab, where you can have different apps for testing voltage transformer tests and also substation tests. But let's go to the power transformer test. And as you can see here, the different apps are actually arranged in the order that is recommended to do the test. So you have the winding resistance app first, then you have the Demag app, and then the turns ratio, and then excitation current, and so on. But let's go into the winding resistance app because we need to magnetize the core first. So you've seen this interface in Tony's presentation, but just to give a brief explanation, in this left pane, you can select the test object. You can choose power transformer in this case, and you can also set the configuration. In this case, we have a YND11 transformer. You can also select whether you want to do the winding resistance test to the primary side or the secondary side, or both. But we're going to select the primary side here. You can also select whether you have an automatic switch box. That is a device that switches automatically between taps and phases. In the center pane here, you can select whether where you have your tap changer. We have it on the primary side, and we have a on-load tap changer with 19 taps. In this pane, you can select the test current and also the winding temperature to do compensations. It's generally recommended to have 1 to 10% of the nominal current. In this case, we've selected 5 amps. Then we need to use the 16 amp generator. We also have a 1 amp generator, but that is too little for this test. You can also select whether you want, how you want the tap operation to work, but we'll go for fully automated for this test. And when we've done our tests, we will have all the results presented in this table but let's do a winding resistance test. So you can see here we start applying a voltage up to it's up to 47 volts, which is the compliance voltage of the tracks is 50 volts. And now we've reached 5 amps, the set value, and we're waiting for stabilization. And that we got the value was stable. So we changed taps to the next tap, and we're waiting for the reading to get stable again. And you can actually set the stability. I think I put it to 99.85% here to make it a bit quicker. You can actually set that value to what you want. I pressed stop there, and when you press stop in the tracks, the winding is automatically discharged to release the energy that is stored in it so that you don't get hurt. You can see here we have the results for the different taps. We have tap 1, tap 2, tap 3, and we had about 324.3 milliohm for tap 2 and 0.7 milliohms for tap 3. And in the bottom edge here of the screen, you can see that we have a button where you go into the demagnetization instrument. This is arranged in the same manner as the winding resistance instrument, and the idea is actually that you can be familiar between, that you recognize. You don't have to, have you learned one interface, you can use all the instruments and tracks. You see, we have the same generator and the same start current put in here, and we need to enter the resistance value that was measured. So I put 0.324 ohms in there. Yeah, I don't know why I took so long time doing that. My apologies. As you can see here, we are going to do the demagnetization on the center leg of the transformer. And let's press play. And if you press this curve here, you can curve icon, you can actually get a live recording of what the demagnetization looks like. This is the same diagram we had before. You go up to the saturation point, you go back, it pauses a bit on the y-axis, and you go to the negative saturation point again, and it bounces back. And now it's going to pause a bit here on the remanence point, and then it goes back to a lower value, and it goes, well, so it bounces back and forth in this hysteresis loop until it reaches the center of the diagram. Their tracks found that it was good enough. We can check the results. So it took 41.49 seconds. We had a remanence of 11.82% to start with, and we have a remanence of below 1% after the demagnetization. So, and if you want to do more tests now after it's the transformer is demagnetized and more or less primed for more testing, you can actually go down to the bottom of the screen and press, and this is the transformer turns ratio test that you go into. So that was the demonstration of how demagnetization is done in tracks. And that actually concludes my presentation. But it's always, if you take one thing from this presentation, is that you should always demagnetize, and you should always pay attention to the order in which you do your measurements. So, any questions, Steve?
Yeah, there's a few questions that's come in, Per, if you wouldn't mind answering. So the first one, should the magnetic balance test be carried out before or after winding resistance?
It should be done after, because if you have you will get it, you could do it before, there's no harm to the transformer, but you will get incorrect results if you have a remanence, a remaining magnetization in the core. Since, well, it's magnetized, and you'll get strange results. So please do it before.
Okay, great, thanks. The next one is, how bad for the transformer is the remanence flux?
How bad? Yeah. Well, the remanence, I think the reason, as I said, the reason with the remanence is actually when you operate the transformer again after having had it shut down, you can actually, the inrush current, it probably survives, but I wouldn't gamble on that, especially if it's sort of, you can get very high inrush currents if you have a magnetized core and you power up the transformer again. So it's hard to say how bad it is. It doesn't always happen, but why risk it is my view on this.
Okay, thanks, Per. And just one more. Can you explain the ferromagnetic materials when the core becomes saturated?
Well, basically, if you see a ferromagnetic material as tiny magnets, and so steel, as is used in a transformer core, is basically tiny magnets, tiny dipoles that are they're in random order. But when you apply a very high magnetic field and they align, all these dipoles align, and then when they are aligned, there is no sort of, let's call it resistance. For a lot, it's hard to use that word when you speak about electricity, but there's no way of there's no resistance to if you apply more magnetic field on that material, and from that point on, it basically acts as vacuum. So what happens is that the tiny magnetic dipoles in the material, they align with the magnetic field.
Great, thanks, Per. That concludes the questions. So
Okay.
Thank you, Per, and I'll now hand over to Joachim.
Perfect.
Perfect. So, am I visible and you can see me as well?
Yep, we can see you. Yep, if you can just make the presentation mode on the.
On the way.
Perfect.
And you see the correct screen as well, I hope.
Yes.
Good. So my name is Joachim Skoldin. I am the product manager for the transformer segment in the Danderyd factory. My topic for today is the TRAX instrument. Of course, the focus will be transformers, but we will also look into it in a slightly other way as well. But first, what is TRAX and why do we have the TRAX unit? Well, what we hear is that sometimes, and not always, is that you would like to have a multifunction unit. Why would you like to have a multifunction unit? Because it's sometimes easier to use it because you have the same software interface. You don't need to switch between instruments. It's sometimes quicker because you start up or you boot up the instrument, as most of them are computer controlled. So you boot up the instrument once and you have the same set of cables, which actually saves a lot of time when you don't have to boot up the systems, type in the same nameplate values again, and roll out a different set of cables and put the other ones back in, because you might have specialty connectors and all of these things. So you cannot use the other cables for this particular unit. It is also easier to transport, because when you're going to site and you would like to test many things, you only need to bring one equipment and not a multiple set of instruments. Of course, as I said, it may not be the way that you operate. It could be that you would benefit more from single function units because you operate spread out with multiple people. But we at Megger try to make this possibility so you can choose whatever way you would like to operate. So with that said, we made the multifunction unit, and it's called TRAX. And what is it? Well, we're talking about transformers. So it's actually a transformer and a substation test system. When we look at the different transformer tests that it can make, it is very, very strong in the winding resistance capabilities. If you look at winding resistance test, the key parameter when you're defining your winding resistance test is the test current. I'll come back to this a little bit later on, but what we see here is we have a very, very strong or high test current with a very high compliance voltage. So it's possible to make and saturate the transformers very quickly and get a good and accurate test. As Pelle or Per just spoke about, the adaptive demagnetization, it is built into the TRAX. It has got to do with the winding resistance, since when you do this, you magnetize the core and then you need to demagnetize the core so the following tests will be okay, and that when you put the transformer back in service, you will not have large inrush currents. With this said, we try to focus on the easy things to use with the software. So you have a built-in on-load tap changer control. That means when you have a tap changer contact, you can connect the raise and lower contact directly to the front panel of the track system, so you can do automatic testing. As you saw in the video or the demonstration from Per, it actually, when it was finished with the winding resistance, it automatically just changed to the next tap. The tap changer testing functionality is also very, very advanced within this TRAX unit. We have the standard static measurement, we have the continuity, but we also have the DRM, which means dynamic resistance measurements. This we will talk a little bit more about, and we have a good case study and a little bit a better explanation coming in the next session. We also have ratio measurements, of course. Here, when you define the ratio measurements on the transformer, it is very often the applied test voltage that is of importance. And then we have 250 volt, or we can go even up to 2200 volt. So again, it's very, very powerful for the transformer tests. We also have some accessories, which is a TanDelta unit. It's of course optional, which increases the output voltage to 12 kV, and it can make capacitance and TanDelta measurements. These were also mentioned by Tony in the beginning. When we look at those standards, the main test with this is basically you look at the 50 or 60 hertz value. So you take a measurement at 50 hertz and you look at the TanDelta or the losses at that point. But this particular unit has a frequency variation, which can go from 1 to 500 hertz or 505, which gives you an added value, especially when you're testing bushings. This is a topic we will cover later on this afternoon, so I will not talk about that very much, just briefly mention it here, but it gives you the ability to do the ITC, which is another TanDelta feature we have within the Megger companies. ITC stands for individual temperature correction, because this TanDelta value, or the measurement value you achieve, when you look in the standards, it says, okay, if it's below 0.5%, everything should be okay with your transformer. If it's between 0.5 and 1%, something is maybe not so good as you, or not as good as you would expect. Or if it's above 1%, it's a red alert. Now, these values for comparison or for analysis is only valid when your measurement is done at 20 degrees. So any transformer temperature out of 20 degrees gives you an uncertainty. Now, with this frequency sweep that we can perform and the ITC patent, we can individually correct your specific transformer to 20 degrees. So if it's 35 when you measure it, we can use the frequency and the ITC patent to correct your measurement value to from 35 to 20 degrees. So you can use these analysis criteria. We also have a VDD, which is voltage dependency detection. which means if your measurement shows some voltage dependence, we will give you a red flag warning. So you will have a small indication saying, okay, something is not behaving as it should within your insulation system. Together with this, we have a 3-phase switch box, which can be manual or automatic. This is to help you and make it possible to do full automatic testing throughout all the taps for winding resistance and turns ratio and all of this. We can also do the FRSL, as Tony mentioned, the frequency response of stray losses. It is not the FRA, it's the FRSL. A lot of abbreviations, I'm sorry for that, but I try to focus on a little bit explaining the differences between them. We can do the magnetic balance and the leakage reactance, which is also sometimes called the short circuit impedance. We can also do other things than standard power transformer tests. We also have the capabilities for testing CTs and VTs. We can do 3-phase circuit breakers, where you do main contact timing for all 3 phases at the same time with the trip timing, close timing, station voltage, pre-insertion resistors, and all the needed parameters that you do for standard circuit breaker analyzer test sets. We also have the contact resistance, which of course is very much needed when you're doing the circuit breaker analysis. You would like to make sure that the circuit breaker contact is good. You can also use the system just by as a voltmeter or a current meter, or the oscilloscopes and other calculations based on voltages and currents. As I said, it's a multifunction unit which focuses on transportability. So one of the key parameters for this unit is it needs to be below 32 kilograms with a transport case, so you can bring it with you on an airplane. Because if you need to go somewhere far away, you can actually check in your system and you can bring it with you instead of shipping it in advance, being out of your system. So this is one of the key parameters for the multi-function test system. Another important factor that we hear about this time is, of course, the safety features. With this, we talk about interlocks, so you can have safety for any guy or girl, which is on top of the transformer doing connections, while another one is maybe on the ground starting the tests. With an interlock on top of the transformer, you can prevent any accidental energization or start of a test during this time. We have ground loop continuity, making sure that your ground system is okay and you don't have any floating potentials between the transformer and the mains ground. We have green-red flashlights as well as sounds to give you an indication when we are doing these types of tests. So it is important for the testing guys out there. With that said, doing a multifunction unit is not always easy. So there is a challenge in getting all the different units into one system and making it easy to use. Per showed you actually very good how it works, and you have seen the different apps that we have available. So this software itself just sorts the different tests in the order you should use them under the test object that you would like to test. So for the power transformer, you start with the winding resistance, you do the Demag, the turns ratio, and so on. So within the software, you have the guidance for how to connect. You have LEDs on the panel showing you which inputs and outputs that should be connected, all to guide you and help you and make it simple to use. Now, I would like to come back to what Tony spoke about this morning. I have a slightly different angle, but when we look at the different standards for transformer testings, we know that we have the IEC and the ANSI IEEE ones. And if we look at IEC, you have the IEC 60076 standard, then you have -1, -2, -3, all the way down to -18, which is the SFRA standard, Sweep Frequency Response Analysis. Now, when we read these standards, do you see the yellow text? It actually says tests shall be made at the manufacturer's works. So these standards and guides are more aiming, or they are very focused on doing the factory tests. Now, many of us face the problem that the transformers are not in the factory anymore. They have been moved to the field. And when we look at the field tests, there are no real standards. But if we also look at the different standardization organs, I know you have heard of IEC, you have heard of IEEE, and you have most probably heard of SIGRE as well. But in SIGRE and also in IEEE, the active participants make a very, very, very useful contribution to our industry. And what they do is, within certain work groups, they make a lot of investigations. And the participants in these work groups can be me or Megger as an instrument manufacturer. It can also be ABB or Siemens or Brush as a transformer manufacturer. It can be universities or a member of an employee of a large power company as well. And within these work groups, they make a lot of investigations. And these investigations are focused for many, many, many different things. It does not necessarily have to be transformers. It can be breakers, and it can be specific parts within breakers or tap changers or so on. But the outcome of these work groups is usually a technical brochure. And on the sigre.org website, they published the technical brochure 342, which is the sweep frequency response measurement. If I go back and you look at the IEC 60076-18, the SFRA, the Sweep Frequency Response Analysis Standard, it actually has the content from this technical brochure within itself. But this technical brochure has a lot more information. It is much more comprehensive, and it gives you the guidance on what a different fault from a transformer, how it shows up in the SFRA standard, in the SFRA trace. While in this IEC standard, you will only have the guidance on how to connect, what should the performance of your instrument be, and so on. While any types of faults is not covered within this standard, but it is described in the technical brochure. So these are more comprehensive. Within IEEE, you have the same type of structure, but you don't have the SIGRE IC, but you have IEEE, and then you publish it as a guide or as a standard. And in 2011, as Tony Wills described and told you this morning, they published the SIGRE Technical Brochure 445, which is the guide for transformer maintenance. And quick rehearsal, it splits the diagnostic techniques into the basic electricals and the advanced electricals, as well as dissolved gas analysis. Now, the different tests you have on the left side, you have the basic, and on the right side, you have the advanced tests. How does this relate to the TRAX unit, which is the discussion or the topic of today? Well, if we look at the different tests, what they mention as basic tests or basic measurements in the SIGRE Technical Brochure 445 is winding ratio. We can do that in TRAX. Winding resistance, we can do that in TRAX. Magnetization current, we can do that in TRAX. Capacitance and dissipation factor, we can do in TRAX. Leakage reactance or short circuit impedance, we can also do in TRAX. The insulation resistance and the core ground tests are the two remaining tests for the basics measurements that we cannot perform with the TRAX units. When we look at the advanced measurements, the FRSL can be done with the TRAX. We also have the tap changer testing or the dynamic resistance, as well as the magnetic balance. This relates to the whole TRAX system structure. So within the main unit, you have the hardware, of course, but you also have some software packages where we have the basic software transformer package, where all the basic tests except the insulation resistance is included. We have the advanced software structure where we talk about the FRSL, but also the dynamic tests on the tap changer, the magnetic balance, and all these a little bit more exclusive that we can do. We also have an instrument transformer package. If you're only testing instrument transformer, maybe you don't need that functionality, but if you're testing the substation, maybe you would like to do the instrument transformers as well. Then we have the different ratios and the knee points and the burden tests with all the guidance. We also have a substation package where we make a little bit of the breaker analysis and the contact resistance and so on. That is related to the system structure in regards to software, but we also have a lot of hardware accessories. We have the TAN Delta unit where we make the capacitance and dissipation factor. We also have a high current booster, which is not really relevant for testing power transformer. You don't really need 2000 amps in any of those tests. But if you're doing instrument transformers, or if you would like to make some other general tests, the 2 kiloamps could be of interest. But for the switch box, it's spot on for your transformer tests. I'll come back to that one. We also have a line impedance kit where you can measure the impedance of the line, as well as a calibration box. The calibration box helps the service centers with all over the world to give you reliable instruments, making sure that you measure what you should. So for the transformer, power transformer, all the standard tests are winding resistance, turns ratio, demagnetization, excitation current, and short circuit impedance. Those you can do with the switch box is winding resistance, turns ratio, and demagnetization, as well as tap changer testing, I might add. We have a few unique features, such as the winding resistance. I spoke about it and I said the large or high current gives you a faster saturation of large objects. So it's actually gives you the possibility of a quicker test. The demagnetization, it's fast and it's also very efficient or good. The tap changer testing, I will speak about a little bit, but we have a lot of information that we can extract from a tap changer, on-load tap changer, I should say, with our testing capabilities, as well as the TAN Delta. The ITC is a game changer for the industry. For the instrument transformers, you have a wide view of what you can do. You can do ratio, you can do burden on VTs, you can do ratio, winding resistance, saturation or knee point, demagnetization, and burden measurements on the CTs as well. For the substation package, we have the line impedance, where you measure the impedance of the line for the relay settings. So instead of modeled values, you will get a measured value. We have the circuit breaker analyzer, which will give you the timing tests for open, close, close, open, and open, close, open sequences. Give you the station voltage, the pre-insertion resistors, will give you the coil current, and also the graphs for the timing and the voltages. We also have the primary injection, where you will get opening time of the whole system with a high current injection. More than that, we have the manual control, which is a unique tool, and you can just use your different outputs and inputs in your specific way, or you can use them as an oscilloscope, where you have a parameter calculation tool, so you can calculate a capacitance, an impedance, or a resistance based on the voltages and currents you measure or generate. You can just ask us for the recipe. I can give you a specific case here. I went to visit a manufacturer of large inductors that they have on the line for DC-DC current injections. So when they made these inductors, of course, it is just an L, the inductance. They would like to measure the L, but they also know that they have a small resistance within their L, in their manufactured inductance. So they would like to see how big is the R, what is the phase angle between the power factor value of this inductor. And with this manual control, we were able to extract all the parameters they actually needed just by injecting a 20 amp current and measuring the voltage as a 4-pole measurement on the inductor. So we had all the calculations already built in there. So shortly about the switch box. It is an accessory which helps you to connect to all the phases on the transformer. And with this, you can have a fully automated test sequence. So you can go through all the phases and all the taps on an on-load tap changer on the transformer. It can only go up to 16 amps because of the relays inside. But it will give you tap changer testing, make before break, but it will also give you some other on-load tap changer testing if you have that app. It will give you the demagnetization, and will also give you the turns ratio, including the excitation current. The idea with the switch box is you have the tracks on the ground, you put the switch box on top of the transformer. Between the tracks and the switch box, you have 10-meter long cables. 3 of them. And then from the switch box, you can connect to all the phases of the transformer, where you have another additional 9 meters. So you have totally 19 meters of connection. and it doesn't really matter how far away the bushing are located, or the bushing tops, because you have 9 meters from the bottom of the transformer up to the top of the bushing. So you have a very, very large connection possibility with this type of switch box. And then you will have the benefit of the one-time connection and the automated test flow. So it gives you a faster measurement. It's also safer because it's less trips up and down the transformer, and there is no disconnection of the leads in between the tests. So if I give you an example, the 20 MVA transformer, if you do turns ratio and the demagnetization and the winding resistance, we have a total measurement time of 14 plus 17 plus 1 minute. So you can see then slightly more than half an hour, you're done with all the different tests. So what we see with this, it's not really the testing time that is the problem. It is getting all the leads up to the transformer, disconnecting the transformer, and doing all these things around the test, or prior or after the tests. And here you can save a lot with the multifunction. You don't have to set the nameplate values many times. You only run one set of cables instead of 5 different or 3 different for the different tests, and so on. There are some unique features and patents within the TRAX. One of them is the adaptive demagnetization. We had the in-depth explanation of this from Per. So I will not go through this step more than saying, okay, we have it built in. It is fast and it's effective. And when you look at the magnetic balance test, the question before was, should you do it before winding resistance or after winding resistance? I would say like this: for me, the magnetic balance is a test to verify that the transformer is properly demagnetized. So for that purpose, I would do it after the winding resistance. But let's say you would not like to do the winding resistance, or you have no possibility to do the winding resistance test on your transformer, and you don't have the possibility to do the demagnetization. Well, then you don't know the magnetization state of your transformer. So if you do the magnetic balance test, in this case, at least you can have an idea on whether it's close to demagnetized or way off. So that would be the purpose of the magnetic balance test for me. We also have another very, very unique method, which is the dynamic resistance measurement. And this is particularly for on-load tap changers. Here we measure the current and the voltage on the high side and the low side. Now, what does this really mean? I'll show you. I happen to show you a lot of graphs here. Let's go one step back, and then we look at the actual winding resistance measurement. Because when we look at this, we usually see a measurement circuit, which is a current generator, an ammeter, and a voltmeter. And we say, okay, you need time to saturate the core and all of these different things. Tony said it's a 4-wire measurement. Okay. Now, if we look to the top right here, and we see we have our measurement circuit here, or here. We have a current generator which produces a DC current. It goes through our measurement system, which actually has a small resistance in the connection cables, for instance. Now, when we take some current through these resistances, it will give us a voltage. Now, when we come to the transformer, we actually inject the same DC current into the winding, and it comes back through another cable, which of course also can have another resistance. It goes through our ammeter and it comes back. Of course, the current flowing through this system is all the same. Now, when I look at it like this or this, what happens is I put my voltmeter exactly on these bushings of the transformer. And inside my transformer, I have my winding and my inductance. So I have my winding resistance and my inductance. So the current flows through this resistance, this inductance, through the ammeter, and it goes back, and I measure the voltage here. So the total voltage I measure in my voltmeter here is the current times the winding resistance, and then we have the inductive influence of this voltage. Now, our purpose is to saturate the core and get rid of the inductance, the inductive part. So if I have a di dt and I have a DC current, what happens in the beginning? I have zero current. I try to ramp up the current to my set value, which could be 10 amps. And when I am at 10 amp, I have a stable DC current at 10 amp. So then the I dt, the change of current over time, is 0. So my inductance times 0 will of course be 0. So this contribution is very, very quickly 0. But then we have the current times the change of inductance, and the inductance is a function of current and time. So here is our a little bit difficult parameter within the transformer to get a good and accurate winding resistance measurement. So again, we wait for the core to stabilize and saturate, and then this becomes 0, this becomes 0, and then we have the voltage and we have the current, and we can calculate the resistance using Ohm's law. This is just another way of showing it how you connect to it on the transformer, because sometimes these diagrams or schematics are a little bit abstract. Now, when we talk about winding resistance, we will of course get all the different winding resistance values for all the different taps. This is a static measurement, and it gives you a lot of information about the condition of your tap changer. This is the same picture that Tony showed you this morning, and it tells you that, okay, I have a very high winding resistance on phase B on tap 10, which is here. So something is very, very probable. You have a very high probability that something is problematic on phase B tap 10. This is something that you can get from a very static measurement. Now, in the tracks, we have a very unique feature which is called dynamic resistance measurement for the on-load tap changer. Now, if we look at this previous picture where we connected the normal winding resistance measurement, and you have the current generator, the voltmeter, and the ammeter through your transformer, but we look at it like this, and we put this extra voltmeter here between these two terminals, these two, which is the same phase but on the secondary side. So now we have a transformer here. We have the current flowing in the one winding, and then we have a voltmeter on the secondary side. Is this not so clear? If I instead make it like this, so you can see that I have my normal winding resistance measurement circuit here, I have my transformer, and I have a voltmeter on the secondary side. Now, for our on-load tap changer testing, you can see that we have now 3 different measurement parameters instead of the normal 2. So what happens is we measure the DC current, which happens to be 10 amps, and we measure the voltage on the primary side, which is 6 volts, 5.5 volts. This will give us the winding resistance. Now, if we send the signal to the tap changer to switch to the next tap, all of a sudden the tap changer will start operating and our steady current all of a sudden drops. Something is happening to the voltage on the primary side, but it's a little bit inconclusive. But the voltage on the secondary side all of a sudden gives you these specific step voltages. From these parts, we can actually calculate the starting time of the tap changer, the different resistance values or the different timing for the resistance values, the total operating time of the tap changer. We can give you the resistance values of the winding, and at the same time also give you the values of the transition resistors. We can also give you the dynamic current, which is this DC current, which is usually called ripple and slope. If it's unclear, I know that Olle will give you the information about this in the next session. So I will not go very deep in details, more than telling you that when we add the extra voltmeter, we have the possibility to identify times, resistances, as well as the dynamic currents. I told you about this, the individual temperature correction. Normally, you measure at the a temperature other than 20 degrees when you're in the field. But then you can measure this small frequency sweep from 1 Hertz to 5 Hertz, and then you can use this particular frequency behavior to predict the temperature behavior. And then you can actually use this temperature behavior to get to the 20 degrees value. And a more illustrative picture is actually this. So what was done is we had a transformer. It was 21 degrees. We measured the tan delta at 21 degrees. And then we made the frequency sweep. From the frequency sweep we made at 21 degrees, we predicted the temperature behavior of this transformer. This is the purple line. The purple line is, of course, hidden behind the other ones here. We heated up the transformer to 27 degrees. We measured the tan delta at 27. We measured the different frequency behaviors, and we predicted how the transformer would behave over temperature from that frequency measurement. And it's this black line. Here you can see a little bit of the black line, but otherwise you can see it's actually the exact same one here. We repeated the procedure for 34 and 49 degrees, and you can see that all 4 temperatures predict the same temperature behavior, and they are, when you look at the measured values at those different temperatures, of course on top of the predicted line. Now, previously, you had a temperature correction curve or a table saying that, okay, if you measured your tan delta at 50 degrees, you should multiply your measurement value with 1.9 to get to your 20-degree value. Now, using these correction factors gives you an error in the estimation based on the actual correction table is not relevant to the specific transformer that you're measuring. Now, this temperature correction can be done for all transformers at all times. And what's worse or good is when you come back to the transformer and you measure it the next time, 1 year later or 5 years later, of course, the insulation behavior has changed, the insulation has aged, and then the temperature correction would be different. So at that time, you take a new frequency measurement and you look at the temperature behavior at that particular time. So even though you have determined the temperature behavior for your transformer once, it will change. But the good thing is you can always find it out using this ITC. We also have the voltage dependency detection. I assume I have taken a little bit too much time, but I will just go through this very, very quickly. When you measure your tan delta, very often you measure it at 10 kV. So here you have 3 bushings, 1, 2, 3. They were tested using 10 kV. They had very, very similar capacitance, and the measured tan delta is well below 0.5%. So everything is fine. Remember, below 0.5, it is okay. Now, for this mid phase, we can see we have a small red warning alert here, telling us that, oops, something is not okay here. We have an indication telling us that we have some kind of non-linear behavior. Can you please make a voltage sweep or a tip up on this bushing? So when you take the same test again, you change the test voltage from 10 kV to 2, 4, 6, 8, and 10 kV. You can see that for bushing 1 and 3, the tan delta value is exactly the same, independent of the applied test voltage. But for the second bushing, when you apply 2 kV, the actual tan delta value is much higher than what it is at 10 kV. And if I measure, then I have 1, 2, 3, 4, 5. So actually at 2 kV, it is above 0.5%, which is some kind of warning or alert. But when I increase the test voltage, the actual measured tan delta value goes down, and indicating that something is not good within this insulation of this bushing. At this particular case, it's very often some kind of connection issue, some kind of resistance in series with the capacitance. This is completely irrelevant if you always make the tan delta test at 2 kV and 10 kV, which some of the testing companies do there out in the world. But if you only measure at 10 kV, you have an extra warning telling you that something might be problematic within your insulation system. So it's a clever way of helping you. with that, I will leave the track system and open up for questions for this. Do we have any questions?
Yeah, we have a couple of questions if you wouldn't mind answering them, Joachim. So the first one is the track supported by PowerDB software, and how easy is that to use?
The PowerDB software can open the track's measurement files. You cannot control the track system from PowerDB like you can do with the Delta 4000, for instance. But you can use the PowerDB to open your files, store your measurements in the PowerDB software, and get the PowerDB report.
Okay, thanks. The next question is, can the tracks really output so many watts, and can it be powered from single phase mains, or does it have to be from 3-phase mains?
Good question. It all depends on what you're testing. The normal transformer testing applications do not require so much power, so it's no problem testing it from a standard 10 amp mains supply. But if you're doing a 2000 amp test with a booster, for instance, the power capabilities within the tracks is between or close to 6 kilowatts. So the actual current needed from the mains is more than 16 amps. If it's short time, we will be able to take that much out of the normal mains, but you need for sure a 16 amps power supply, and you cannot do full testing for a very long time, because then you will take the fuse. Then you need a bigger 32 amp supply.
Okay, great. Just one more question. How can I overcome incorrect tan delta measurements in high humidity areas like coastal regions using the tracks, and how durable is the tracks?
When we look at high humidity responses for tan delta, there are two different ways of measurements. It's the same with the insulation resistance. You can measure between high and low terminals, which means you measure the capacitance from high to low, or the insulation resistance from high to low. Then you're measuring between two terminals that are independent from ground. And the problem with the humidity is it gets stuck on the bushing surface, and all the voltages and all the currents going from the high side or low side will go along the surface of the bushing down to ground. Now, if the ground is put on guard potential, all those currents will be discarded and you will have a very good measurement. So the measurement between high and low will not be affected by this humidity, high humidity. But if you measure the capacitance or the insulation resistance from high to ground, you will of course get all these surface currents or the creepage currents along the surface of the bushings included in your measurements, and they will contribute to this. So what you can do is put a guard strap on all the bushings. That will help, because then you can eliminate all the creepage currents from this one. It requires a little bit of extra work, but you can also make sure that your bushings are clean. So a good procedure for tan delta testing is to clean all these bushing surfaces, to making sure that the surface currents are eliminated as much as possible.
Brilliant, thanks, Joachim. So that concludes the questions for this session. So I'll now pass over to Ole.
Good, thank you.
Okay, hello everyone. Now you will see my cam, looks like. Perfect. I will now try to share the presentation. So sharing, we take play and monitor 1.
That's it. Yeah, if you can just make it presentation mode, that would be great.
Yes. So we start the slideshow, and now I think everything is okay, right?
Perfect. Yeah.
So welcome to this fourth presentation and right before lunch. So I guess this has been quite a long morning. I'm the last Swede to talk. After the lunch, we will have a colleague from Valley Forge and also Lutz, who is an application or system manager in Germany located. So today we're going to look into OLTC case study, but my idea was if I only present the case study, you might not fully understand it. So I will do some theory on OLTC and DRM, and then we will go into the case study. So hopefully we can learn a bit, and I will just start my timer so I have some idea. So for today, like this is what I intend. So we look into the on-load tab changer very quick, which is relevant for us, the parts. We do a very quick recap of winding resistance measurement because the dynamic resistance measurement and winding resistance measurement are so strongly linked together. So it's good to have that focus clear. And I will just pointer option. And then we will focus on our way of making dynamic resistance measurement. So if you've heard about DRM before, then maybe you should pay close attention to this true DRM because there's a lot of interesting details there. And then we wrap up with the case study where we look into an actual case. Hopefully we have time for some questions as well, but at the end of this day, we will have like an open questions house as well, where everyone, all the presenter can answer questions. I hope it'll take around 35 minutes, but I guess a bit more. So let's start. So why do we even have an on-load tab changer? I mean, the load is not constant in our grid, like of magnitude, but also of phase angle. So as a result, the current will be different. And you know, current is different in your power transformer. The voltage drop inside your power transformer due to the leakage reactance or the winding resistance will be different. So as a result, the voltage is not constant. And in a normal grid, you want to keep the voltage stable. And this can be done by different ways. So you might have a voltage regulator or like you insert inductors or capacitance in the grid. But another option is to use an OLTC. And this is, of course, brings the regulatory winding into consideration. So due to that the current is not constant and the load is not constant, the current and voltage will vary. So we need to have some type of regulatory ability. We do this by taking, in this case, the primary winding, taking and decide it in two parts, a main winding and a regulatory part. The on-load tab changer is connected to the regulatory winding. And the regulatory winding is split in many different sections, where each section has a certain amount of turns. So you can add or remove turns on your primary winding, meaning you will adjust the magnetic flux in your power transformer. So in each of these positions are called tabs. So the OLTC will connect different tabs of your regulatory winding in your circuits. So this way you can modify the turn ratio of your power transformer. If we just look on the OLTC, like during operation, what happens or what criteria we have, it's quite logical to understand why they're designed as they are. So the first criteria we have is that the current has to be continuous. So if we want to go from one tap to another, the current has to stay continuous. If not, it will be, we'll have a quick blackout. So this creates this make before break criteria, meaning if I go from one tap to another, I have to connect to the tap I'm coming to before I leave the one I'm currently on. And this criteria means that two taps will be connected at the same time. And these taps correspond to different voltages. So this means you have a voltage drop between these 2 points. If you have voltage between 2 points, you will have a circulating current there. It will go a current. And this current needs to be handled by the on-load tab changer. And that's the need for some type of transition impedance. If you only short circuit those 2 points, you have a very, very high current. So why we have an OLTC is quite logical, and also why you need this transition impedance is quite logical if you just follow all the steps that is required. So we just start with a boring definition. So IEC 602.14 is the standard for tap changer, and here they just define it as a device that is capable of changing the taps while the power transformer is energized. And it can also be called LTC, so OLTC, LTC, on-load tap changer or load tap changer. That's the same thing. I will now just introduce like the two common design types, so to say, so we get a bit more familiar with the OLTC. So the most common one I would say is a diverter switch and tap selector. So here we can see just a very rough idea how it looks like. This is an actual diverter switch and tap selector. So up here we have the diverter switch, down here we have the tap selector. Here we have the electrical schematic of the same thing. So the tap selector will have two arms. One is connected to the load current or the current tap in use. The other is not connected at all. And this tap selector is free to move up or down, depending on which tap you want to go to. Then we have the diverter switch. It's this part and it's located in upper tank. Inside the diverter switch, we have arcing, and we have several other mechanisms as well, of course. But a critical component is like, how do you handle the arcing? Because you have some, in this case, it's just a symbol, but you have this, what is just symbolized as this lever mechanism. So you have some energy that charges up this lever, and it will travel from this tap all the way to this tap, while at the same time connecting these transition resistors. We will go into this in detail, but when it disconnects this point, there will be some type of arcing. So here also these transition impedances that will limit the circulating current between this and this tap. Another type is if you take the tap selector and diverter switch and put them into the same unit, so to say. This is called a selector switch or an arcing switch. And these are maybe more common on smaller power transformers. And here's just an example how it might look like. So then you have something that carries the load current, and then you have the transition impedances connected at the side. And here is how it looks in reality. Obviously, this would be filled with oil, so the arcing will take place inside this oil environment. We have one for each phase, but they are operated by the same mechanism. So this mechanism is driven by a motor that will store up some energy, and then it will be released through some spring, and then that mechanical power will be transferred, so this can rotate, or this part will rotate. We can also see the transition resistor here, the springs, and we have the each tap connection here. And another big classification of the on-load tap changer is like, how do you handle the arcing? And it can be in vacuum or in oil. So oil is was the common method for 20 years ago maybe, but today like the vacuum technology is the superior technology, so it's the most common one today for new OLTCs. And obviously this is in the diverter switch. You have the vacuum tubes then that will handle the vacuum and the arcing. So this is a key classification, but from our side, when we try to diagnose these from this type of test, it doesn't really matter. The position of the OLTC is also critical, so it can be on the secondary or the primary side. If it's on the secondary side, it will need to deal with a much higher current, and then different technologies might be used. But also, like if you have a delta winding, you might have 3 OLTCs or you might have 2. For an auto transformer, it's also hard to position only one OLTC, so then you might need to have more as well. So the position of the OLTC is also an important parameter. So I talked a bit about these transition impedances, and generally there are 2 types, a PA, preventive auto transformer, or a resistor. The main focus will be resistor principle, because these are most common in Europe, while the preventive auto transformer are common in the USA. But of course, the number of resistors that is connected here can be 1, 2, 4, or 6, or maybe more. There's different solutions here. But here we can just see this circulating current that I'm talking about. So both of these taps are connected during a short period of time. When they are, it's a voltage drop between them, so a current will go. Of course, the load current or our test current will take this path, but we will have a circulating current inside this OLTC. And here it's limited by these two resistors. In a PA, it's a different type of construction, so it will prevent the circulating current, meaning you can operate in this bridge position. But the focus going forward will be on this resistor principle. So we will do a quick recap of winding resistance now, but also introduce the DRM, because it's only 2 slides with VRM, and I didn't want to have another one of these. So quick recap, winding resistance measurement. We need a DC source, we need a voltmeter, and we need an ammeter. This is the circuit. We connect them and we measure the voltage at the winding. Of course, it will take some time before we reach a stable state, because we need to magnetize this core, and we have an inductance and etc. How long this take will depend on several parameters: test current, how large the transformer is, vector group, magnetization since before. But in general, it will take some time. Another important part of the VRM test is the discharge and demagnetization. So in VRM, we apply a DC voltage to an inductance. This inductance will store this energy. So when we try to shut off the current, almost all the energy will come out, and that's what we call discharge. Some energy will be left, and that's the remnants. And for winding resistance, we test all the taps on each phase, and then we compare them with each other. So like tap 1 for each phase is compared, and then tap 2 for each phase is compared. And normally when you perform the winding resistance measurement, you test one phase for all the taps, and then you go to the next phase, test that phase for all the taps, and then the last phase for all the taps. And the reason for this is that you can then keep the current on throughout the whole phase, so you don't have to turn the current off. If you were to test phase A for each of the 3 phases, you would need to discharge the power transformer between each phase. So normally you test one phase for all the taps, and you just keep the current on. So when we go from one tap to another, because we're keeping the current continuous, we can record how the current will change when these transition impedances is connected. And this is the dynamic resistance measurement. So it's a very natural extension of the winding resistance test. We just look at the current when we make a transition in its simplest form. So let's look at this dynamic resistance measurement. Here we have this regulatory winding, we have 2 tap selectors, we have these transition impedances. In this case, we have 2 resistors. Here is this diverter switch. So right now we have tap 1 connected, and the load current follow this red path, or our test current. I mean, in this case, we have this test, so this is our test current. We tell the OLTC to make an operation, the motor will start to work, and it will release its energy, and this will start to travel. Again, this is just an illustration. Normally it doesn't look like this. You have different, like 4 contacts that is connected, but it's a good illustration. So at phase A, this will start moving. At some point, we will connect the first transition resistor, and once we have done that, after another time, we will disconnect this part. We will have some arcing here, but this one will continue to travel, and we will connect both in parallel, the transition resistors. This is the make before break that we have to connect to the tap we're going to before we leave the present. After some other time, we have connected this secondary transition impedance, and finally we have managed to go from one tap to another without interrupting the current. Also in this state C, we have this circulated current that these are made to limit. If we look at our current during all of this, we have here in state A, we have this stable state. We can perform the winding resistance test, and this is an inductance, an RL circuit, and we have a DC in time, so to say. So this means that when we connect another resistor to this circuit, it will no longer be stable. and we will have some time constant determining what the current will do. So the current will drop here because the power or the voltage we apply from the instrument is still the same, but we have more resistance now, and then the current has to decrease. When we have these two in parallel, we will have a lower resistance, so the time constant will be a bit larger, so the slope of how fast we are dropping will decrease. Again, when we have one resistor, we will have a bit higher time constant, so lower time constant, so it will drop faster. And here at the final position, it will go back to a stable state again. So we will just define something that is called the ripple, and it's just a measure of how much does the current drop through each transition. So if this would be 100%, we would maybe have 95% ripple here because the current goes almost to zero. So this would indicate a problem. But also here we can get some timing from the exact moment when the current starts to decrease until we reach this bottom value. We get the timing of the OLTC. And of course, we also get this current graph. And the idea is that you make this for all the transitions, for all the three phases, and you have a lot of graphs and a lot of different numbers that you can use to diagnose the OLTC. So this is what I call a quick guide for dynamic resistance measurement. I don't have very much time today, so I just put a lot of good things to know in this slide. So first off, we have this time constant that I talked about, and this will determine the response. So this tau is the inductance divided by R. And this can be modified. I will talk about it very soon. And DRM in general is quite a new test. I mean, it's maybe 30 years old, but in our industry, it takes a long time before a test gets recognized or established. So as a result, it's not very well defined in the standards today. And also, as a result of this, it's quite many different types of tests on the market. So there are different ways of performing DRM. We can have the secondary side open, so we have the exact same circuit as we have for winding resistance measurement. One can also short circuit the secondary side, and why you would do this is because if you short circuit, you will reduce the inductance, and this means we have less inductance, meaning the current graph will be a bit more sensitive to any changes because we have a lower time constant. So in this way, we can get more information, so to say, about the OLTC by short circuiting the secondary side. Of course, it might be hard to do the winding resistance test at the same time. The third option is to replace a voltmeter at the secondary side, and this is the foundation of our method. So the focus will be on this and this type of technology. And of course, all of these will produce the ripple that I introduced, the timing and the current graphs, and all of these are used as diagnostic. So sometimes it's enough just to look in the ripple. If it's some problem with the motor or some like this moving mechanism, it might be the timing. And also in the current graph, we might see if there is a connection when it shouldn't be, or etc. So different type of fault can show up in different parameters. We from Megger, or with this track system, uses something that we like to call true DRM, because dynamic resistance measurement give you a current graph. So like dynamic resistance measurement, but we look in a current graph. But with our DRM, we look in a resistance graph. So that's why we like to call it something else, because now we actually look into the resistance. So the focus now will be this true DRM. So this is the toughest slide in my presentation. If you understand this, you will be all fine. If you don't, I mean, it takes some time to get used to this. So it's okay. So here we have this connection we have for the DRM. We have a DC source. We have a test current that is being measured. We have a system here. This is the DC source internal resistance. It's the ammeter. It's the cables. You know, the system. We have the winding resistance. We have a large inductance here, the power transformer. And then I have a resistor here that is grayed out. This is this transition impedance, the transition resistor. So it's only connected for a short period of time. And then we also place a voltmeter on the secondary side. So in the first case, everything is stable. We have a stable I and a stable voltage at U1, and this is not connected. We now insert this resistor into this circuit, and as a result, it will no longer be stable. The charged up energy in this inductance will try to prevent this current from dropping, so it will induce a voltage. So it will be a voltage first driving the current through the resistor, but also an induced voltage of the winding to try to prevent this current change. That is depending on the resistance value. This voltage that is induced to try and prevent this change is transformed, it's a transformer, to the secondary side where we can detect it. Of course, with the scaling factor of the power transformer kept in mind. And this process is true during the whole operation. So if the R transition would spike, let's say there's some bounce or something, in that instance, this inductance will induce a higher voltage because the current will try to drop even more. So this happens in real time, like throughout the whole operation. So we get a very sensitive method. So this voltage will in some way replicate exactly what is happening with this transition resistor. And from this, then we can get these DRM graphs that we look at as an analytic tool. So it's some steps happening here, but in general, we're just connecting a new resistor to our RL circuit that is in stable state. So, and then we have a power transformer. So as a result, we get these types of graphs that we like to look at. So first, the resistance is 0 because we are in this stable state. We connect, in this case, we have two resistors. We connect the first resistor, and of course, this will be some resistance. After a while, we connect them in parallel. We will have a lower resistance, and in final state, we will connect only the secondary resistor, and it will increase again, and eventually it will reach 0. So the time frame here is 40-60 milliseconds because these resistor types are very fast, else they will overheat. So how do we get this graph? How do we come from here to here? Well, we have some equations. U1 is the voltage we measure, and then we can just apply Ohm's law in the primary side of the winding. So we take the current times the winding resistance on this tap that we just measured. We use the induced voltage on the secondary side to know the voltage of the inductance inside the inductance. So, and also of course with the turn ratio, and also we have some voltage over the transition impedance to drive this current. This one we measure the current, we have measured the winding resistance, we measure the voltage on the secondary side, we know the turns ratio. As a result, we can determine the voltage across the transition resistor. And of course, the resistance is voltage divided by current, and as a result, we get the resistance value of the transition impedance. And this equation is true through the whole operation. That's why we get these types of curve. Because when we connect both in parallel, we will have less resistance, so the induced voltage will be a bit lower. So the voltage corresponds immediately to the transition resistor. So this is how we end up with these type of graphs. So what is so good about these graphs? Well, as I said, this ripple parameter that is quite common to use as a diagnostic tool, it depends on this tau constant, but the tau is not constant. So if you have different instruments, you will have different resistance in your circuit, meaning it's hard to compare different measurements with this shutter because the graph will look a bit different depending if you use this instrument or that other instrument. Also the length of the cables. So to use this normal current graph that is a bit sensitive to these parameters means it's hard to compare different measurements with each other. With the true DRM, this resistive curve that we get, it's the same for all instruments because we only look at the voltage over a transition resistor and the current. And this doesn't depend on the system resistance. We also get the values of these resistors, so you can compare with the nameplate, which is a good way to just make an easy nameplate comparison when you're in the field. And also, I talked about when you short circuit the secondary side, you lower the inductance, you increase the sensitivity. So sometimes it's a bit of a discussion about this, like sensitivity, open versus short circuited side. We would have the best sensitivity because basically any change we can detect, while the inductance will prevent changes in the current graph, however you do. So all of these three arguments, we believe, makes this true DRM the best DRM method to detect problems. And here's just another example of this type of graphs that looks a bit more non-perfect, so to say, just to show you like the kind of things we capture. So this instrument tracks that Joachim talked about, we do this called step by step. So we perform winding resistance, then we do DRM, we do winding resistance, we do DRM and winding resistance. So as a result, the DRM is not a new test, it's just part of the winding resistance test. Like, we're not asking you to add a lot of extra testing time, because the only thing you need to do is go back and measure the secondary or the resistance of the winding that don't have the tap changer on it. So it will add a very, very little testing time. So you need to do 3 more measurements on that winding. But besides, like, what you gain from it is that you gain the winding resistance, the dynamic current graph, and the resistance graph. You get this resistance value of the transition resistor. You get the transition time for a tap changer in each state. You get this ripple, and it's also possible to connect a current clamp to the OLTC motor and see how the motor operates for each transition, so to say. So with a small amount of added test time, you just get a lot of information about this OLTC that you might not know anything about other case. So absolutely amazing in my opinion. So that's what I'm trying to convince you guys. So let's jump into this case study. So first, a quick shout out to Megger Technical Library, where you can find this case study. It's just on our webpage, and I think anyone has access to it. You just need to register an account. And in there, like, all my colleagues in marketing and different factories and application engineers produce documents that covers like a wide, like our whole product range and the things we measure on. So for the curious reader, you can learn a lot. So Megger Technical Library, you can also find this case study that I will just go over now, because now we understand this DRM technique, so everything will be familiar. So a bit background, this was a quite small unit, 25 MVA, 132 to 11.5 kilovolt, 3-phase transformer. END1 was the vector group, and it was used as a backup unit, so hadn't been connected to the grid for a few years, and now they wanted to move this unit to where it was needed in another substation. So before they moved it, they did some diagnostic on it to make sure it was fine. And this happened in Iraq, and the type of on-load tap changer was MR, and then MS was the type. But MR, of course, is the largest manufacturer of tap changers, so I think everyone is familiar with that one. So they performed like the basic tests. So first they did the winding resistance measurement, and here we have the 3 phases plotted together. They also made some temporary correction, and as I said, we compared the phases with each other, and it was a very, very small variation. The maximum was 0.26%, and of course in the standard they say that 2% is the maximum allowed. So this is no problem at all. Then did this transformer turn ratio, and again, nothing is wrong here. Sure, one phase has a bit higher error, but maybe that was in the design, and also it's below what would indicate a fault, 0.5%. They then performed this leakage reactance or short circuit impedance or short circuit nameplate impedance, whatever you like to call it, but basically you short circuit the secondary side and you just measure the impedance of your power transformer. So we can see that even here, no error to talk about, not any indication of a problem. So we then move on with the Tangens delta measurement. Of course, this is very common. Quick shout out to ITC2, the temperature correction. And again, no error to see about. We have this nice frequency curve. So, and if DRM didn't exist, this story would end here. So it would be a very bad story, but luckily they had the opportunity to perform dynamic resistance measurement along with their winding resistance measurement. So let's look into the ripple. So the ripple was this parameter, how much the current drop for each transition. So for two of the phases, things look super stable and super normal. But then in phase B, we can see that, I mean, what's happening here? We have 100% ripple, means that the current goes to 0. We don't have make before break. But also for each transition, it seems very strange that it's first off so much higher, but also that the value will vary in between different transitions. So going deeper here, we look into this resistance curve. This is for phase A, the healthy, so to say, one of the healthy phases. So this is what we can expect from like a service-aged OLTC, let's say it like that. Some type of bouncing here, maybe some like contact happens here. Maybe this is the main contact disconnecting, because normally you have two contacts, main contact and arcing contact. Same with, and so this looks completely normal. Then we go to phase B, and now we see like, okay, here we had 11 ohms or 12 ohms in the, but here we can see something completely is happening. The resistance is not constant throughout the operation, it varies a lot, and at the end it increases to what seems to be like 300 ohms. Again, we don't measure this resistance, we only measure the induced voltage on the secondary side. So there is apparent resistance, so to say. But as soon as we connect them in parallel, it goes back to this stable value we had before. And then when it's only the secondary transition impedance, everything is stable. So this can of course be seen on all the transitions, and one can tell more about this, but the conclusion was that part of this, or one of the arms of the transition impedances, didn't make proper contact, or it wasn't connected in the proper way. So from this, they decided to remove the diverter switch. So the diverter switch have its own oil, so they could empty that of oil and just disconnect it and lift it out. So here is the diverter switch before it's cleaned, and then they clean it off and it looks much nicer. So they found this contact that was loose. The welding had been a bad welding, or something had happened. It had cooked, so it had loosened. And here we can see the similar contact for phase A, I think. So this contact was disconnected, while this wasn't. So here we have like this transition period that we looked on previously. We started tab 1, we go to the first transition impedance, but this wasn't the case. So it looked more something like this, like kabam. This one wasn't properly connected here. Like sure, there's still some type of connection. Maybe it was just it wasn't properly connected here, but it still made some contact, because we still saw some resistance. It wasn't constant. But here, something was very fishy with this contact, causing this problem. And I mean, they had removed the diverter switch, so they just welded that contact back into place, installed it, put back the oil in, and then they performed a DRM test for this same transition. And now it looks much more like phase A, and everything looks normal. So as a conclusion, or in this case, it was they could fix it, so to say, on site, and they found the problem. And that was the end of the case study. I mean, these case studies, we have a few on different topics, and we like them to keep like very short and consistent. This was the problem, or this was the background. They did these measurements. This was the problem. So this is how what DRM can be used to detect this type of problems. So as a summary, like the on-load tab changer is a critical part of the power transformer, and it will continue to be that. And it will also use this mechanical part in a long time, I think. Like there is no electrical, so to say, OLTC yet. And DRM is a great way of testing the OLTC. You can find mechanical problem, but also electrical problem with these transition resistors. And the DRM test itself doesn't add a lot of extra testing time. Like, we don't ask you to take that much more time. You perform it when you do the winding resistance. So you just collect much more data and just start doing DRM and like share your findings, because we as an industry need to learn more about this test. And for like each case study, etc., we will build up the knowledge and we will be better to say what the problem is. So thank you very much, and hopefully you have some questions. Yeah, this is the instrument, but Joachim talked about it. So now questions.
Great, thanks, Ola. There's a couple of questions come in if you don't mind answering. Will the DRM measurement be included in any standards?
So SIGRE right now have a working group working on OLTCs, and part of that is DRM. Also, they're making a new field testing guide in IEEE, and also DRM will be part of that in an annex. So it's coming into the guides at least. So yes, it's coming.
Great, thanks, Ola. Just one more if you have time. Can the test be fully automated with tap changer control?
Yes. Same with VRM. You connect one time, you connect the switch box, you press play, and you collect your data.
Perfect. Okay, that concludes the questions, Ollie. So thank you very much for your time. We're actually going to take a 30-minute break now. So I will I'll put some videos up just for the half an hour. If you want to, enjoy a sandwich or something and watch the videos, feel free. But we'll be back in 30 minutes. So so hopefully you stick around.
Transformers and their bushings are important and expensive assets in electrical power networks, and they've become among the most mission-critical components in the electrical grid. Knowing the condition of the transformer insulation gives a correct input for risk assessments and asset management. Among other effects, high moisture content limits the loading capability, decreases the dielectric strength, and accelerates the aging of the paper insulation, thus reducing transformer life. Dielectric frequency response measurement, DFR, is a cost and time-effective method to determine the health of the transformer, including the moisture content of the oil paper insulation system. It's important to understand that almost all the moisture in a transformer is in the paper, not in the oil. Typically, more than 99% of the moisture in a transformer resides in the cellulose insulation. Therefore, the traditional method of inferring cellulose moisture content by measuring water content in the oil is much less accurate than using DFR measurements to calculate moisture in the cellulose. The test is easy to carry out. Connect 3 cables. Enter the insulation temperature and start the test. When the test is finalized, the data is automatically analyzed and presented. Several international standards offer guidelines for insulation assessment in terms of power frequency tan delta, moisture content in the solid insulation, and conductivity of oil. Referring to these standards, IDAX provides the user with a thorough description of the insulation condition. Measuring dielectric response at very low frequencies takes time. In the new IDAX, this issue is addressed by introducing a new and unique method where the test signal at low frequencies contains a combination of frequencies. This method significantly reduces the measurement time in the low frequency range and, consequently, the total measurement time. As an example, an IDAX measurement down to 1 mHz requires only about 22 minutes, the fastest DFR test available. without compromising the accuracy and reliability of the frequency domain measurement technique. Diagnosing the moisture content accurately in a power transformer is a very important tool in condition-based maintenance. The first IDAX model was released in 1997 and was the first test set for performing DFR testing in the field. Since then, IDAX instruments and the DFR methodology have been used by numerous customers globally. The methodology and technique have been refined over the years, and the 5th generation IDAX is the most versatile DFR instrument on the market. Fast, easy to use, and provides automated insulation analysis. To summarize, Mega offers the fastest and most user-friendly DFR instrument in the market, featuring AC measurements for high interference immunity, multi-frequency technique minimizing measurement time, individual temperature correction of dissipation factor, and automated measurement and insulation assessment. To learn more about DFR Made Easy, do visit us at mega.com/tx.
Today's modern world functions on electrical power, and its availability is taken for granted. Transformers are crucial assets in the electrical systems, helping to deliver electricity in a dependable and efficient manner. Electrical maintenance is a critical factor in ensuring reliable operation. In today's busy world, time to perform maintenance is reduced from days to only hours. It is important that testing conducted gives a clear indication that the transformer operates properly until next scheduled outage. The primary test performed by the Delta 4000 is AC insulation integrity and is completed by measuring the tan delta, also known as insulation power factor. Transformers are divided into two major categories of construction and therefore into two types of testing, mechanical and insulation. Today's focus will be on transformer insulation, as we see this as the main determinant to the aging of transformers. For a typical two-winding transformer, we are interested in three key insulation measurements: high winding to low winding, high winding to ground, low winding to ground. Some newcomers to this test assume we test between phases, but it is between windings where test is conducted, as well as winding to ground. Preparations and connections. Remove all connections to the transformer bushings, including lightning arresters and bus bar. Isolate neutral winding from ground connections. We prepare the Delta 4000 by connections to transformer ground. Short all phases for each winding together, ensuring shorting leads do not droop. Connect HV and low voltage red lead to windings. Transformer is now ready for testing. We are now required to fill in nameplate information on our two-winding transformer form. This includes critical information such as oil temperature, required to evaluate test results. Next, we check off our overall test. We ensure that the proper test voltages are set for both high side and low side testing. Once properly set, we depress the test button and test sequence will begin. Once interlocks are depressed, voltage is applied to winding and tests are executed. We can now observe testing as it is automatically completed, noting any unexpected results. We review the results and determine if they are acceptable. We are now ready to test the low voltage portion of the transformer. We exchange the high voltage lead and low voltage red lead on top of the transformer. Ensuring that the proper test voltage is selected for the low side, we now depress the test button, which begins the second series of tests. Once prompted, we close interlocks at appropriate time and test voltage is once again applied to transformer. We can observe the results as they are completed on the dialog box. Once we see the results are as expected, we can confirm good insulation condition of the main body of the transformer. For proper correction of results, we must input correct transformer oil temperature into nameplate info. Temperature can change results significantly, and so correct temperature is critical. Temperature correction graphs place all transformers and bushings into one or two categories, which is not accurate for many of our critical assets. As can be seen by this sample of actual temperature correction for various transformers, results can vary significantly. With the Megger Delta 4000 and its patented intelligent temperature correction feature, we are now confident that the results are true at any temperature we test at. With our busy lives, we seek to do more within our day, and the importance of keeping the lights on is critical. In today's world, power outages are considered significant events which are reported and measured as a society's quality of life.
Megger has been a pioneer of electrical insulation testing since 1885, and today offers one of the broadest portfolios for testing transformers. Commissioning tests and repeated preventive maintenance checks are crucial and often seen as a prerequisite for the safe and reliable operation of power transformers and substations. The Mega Transformer Test Van is a state-of-the-art integrated measurement system for the on-site condition assessment of power transformers. The biggest advantage of the Transformer Test Van solution compared to separate or multifunctional instruments is its immediate readiness to test. All leads are on reels, pre-connected to the test instruments. Software-controlled switching eliminates the need to climb the transformer several times. This results in increased productivity, safety, and user comfort, not to mention the air-conditioned, office-like working environment of the van itself. The rear compartment is separated from the operator compartment by a transparent partition and contains all the necessary cable reels to connect to the test object. The user-friendly connection diagram is immediately visible, placed inside the door to facilitate the setup of cables and leads on the test object. Roll out the respective cables, attach them to the transformer bushings, and plug the cable ends into the output panel of the switch box. All instruments are mounted on racks under the table and, if required, can be easily removed for standalone use with their own accessories. In the core system, 4 applications are integrated. Additional applications are also available. A central touchscreen computer running PowerDB database software can control the instruments and collect the results. The user can select and prepare test circuits through the control unit and continuously monitor all safety-relevant parameters. Insulation tests can identify the deterioration of electrical insulation. High-voltage AC tests measure the dissipation or power factor and capacitance of transformer windings and bushings. Insulation resistance is determined between windings and tank using a high-voltage DC source. Turns ratio and winding resistance are low-voltage tests performed on every winding individually. Usually, they are done to assess the condition of windings, contact points, and the proper operation of tap changers. Winding resistance and ratio measurements should be performed in all tap positions. Remote control of the on-load tap changer simplifies the test routine. Certain tests are sensitive to core magnetization, so demagnetization should be performed after measuring the winding resistance and before returning it to service. An optional power generator driven by the van's engine can provide enough energy to complete all tests autonomously. After test completion, finally disconnect the test leads and roll them back onto the reels. The transformer test van concept combines routine electrical tests and advanced diagnostic techniques to facilitate a complete transformer check in field. Testing with the transformer test van saves substantial amounts of time and helps prevent accidents.
Mega has unrivaled knowledge and experience within the power transformer industry and has been producing high-quality devices for over 100 years. The TRAX transformer and substation test system is a complete solution for transformer and substation testing. This easy-to-transport device has a robust yet lightweight design, which allows it to be transported as check-in luggage rather than cargo, and is easily carried across substation sites. It can perform a number of electrical tests traditionally carried out by individual instruments. Winding resistance, load tap changer testing with DRM, adaptive demagnetization, turns ratio, short circuit impedance, tan delta or power factor, and more. TRAX is easy to learn and use with a single interface architecture for all tests, reducing user training costs. Using a different app for each instrument, the appropriate connections diagram are provided, and only the necessary functionality is displayed, making each test simple and time efficient. It also provides full manual control for custom-defined measurements. TRAX has several inbuilt enhanced safety features, including automatic and fast discharge of inductive measurement circuits after a winding resistance test, dual interlock and ground loop detector, optional strobe warning lights, and optional three-phase switch box for one-time connection, thus reducing the number of ladder climbs. TRAX provides comprehensive reporting for full transformer health analysis, with accuracy equal or better than what is expected from using individual test sets. TRAX is the ideal solution for transformer and substation testing.
Measuring transformer turns ratio has long been an essential test for transformers. Mega's new TTR is designed for harsh field testing environments. At 7 kilograms, the instrument is both tough and lightweight. The new True is so simple to use, only a quick guide is needed to begin testing. Mega provides durable, flexible leads for fast, safe, and most important, easy connection to any size transformer built today. The 7-inch touchscreen is easy to see in both dark and full sun conditions and operates down to -20 degrees Celsius. The display uses large icons guiding the operator to test any type of transformer. At under 10 seconds per test, you will have more time in your busy day to manage other important things. The most impressive part of the True is its accuracy. Our three-phase source gives results that you can trust. Data is easily saved or printed for convenient reporting. Mega continues to provide solutions that allow safe testing with confidence.
Transformers and their bushings are important and expensive assets in electrical power networks, and they've become among the most mission-critical components in the electrical grid. Knowing the condition of the transformer insulation gives a correct input for risk assessments and asset management. Among other effects, high moisture content limits the loading capability, decreases the dielectric strength, and accelerates the aging of the paper insulation, thus reducing transformer life. Dielectric frequency response measurement, DFR, is a cost and time-effective method to determine the health of the transformer, including the moisture content of the oil paper insulation system. It's important to understand that almost all the moisture in a transformer is in the paper, not in the oil. Typically, more than 99% of the moisture in a transformer resides in the cellulose insulation. Therefore, the traditional method of inferring cellulose moisture content by measuring water content in the oil is much less accurate than using DFR measurements to calculate moisture in the cellulose. The test is easy to carry out. Connect 3 cables. Enter the insulation temperature and start the test. When the test is finalized, the data is automatically analyzed and presented. Several international standards offer guidelines for insulation assessment in terms of power frequency tan delta, moisture content in the solid insulation, and conductivity of oil. Referring to these standards, IDAX provides the user with a thorough description of the insulation condition. Measuring dielectric response at very low frequencies takes time. In the new IDAX, this issue is addressed by introducing a new and unique method where the test signal at low frequencies contains a combination of frequencies. This method significantly reduces the measurement time in the low frequency range and, consequently, the total measurement time. As an example, an IDAX measurement down to 1 MHz requires only about 22 minutes, the fastest DFR test available, without compromising the accuracy and reliability of the frequency domain measurement technique. Diagnosing the moisture content accurately in a power transformer is a very important tool in condition-based maintenance. The first IDAX model was released in 1997 and was the first test set for performing DFR testing in the field. Since then, IDAX instruments and the DFR methodology have been used by numerous customers globally. The methodology and technique have been refined over the years, and the 5th generation IDAX is the most versatile DFR instrument on the market. Fast, easy to use, and provides automated insulation analysis. To summarize, Mega offers the fastest and most user-friendly DFR instrument in the market, featuring AC measurements for high interference immunity, multi-frequency technique minimizing measurement time, individual temperature correction of dissipation factor, and automated measurement and insulation assessment. To learn more about DFR Made Easy, do visit us at mega.com/tx.
Today's modern world functions on electrical power, and its availability is taken for granted. Transformers are crucial assets in the electrical systems, helping to deliver electricity in a dependable and efficient manner. Electrical maintenance is a critical factor in ensuring reliable operation. In today's busy world, time to perform maintenance is reduced from days to only hours. It is important that testing conducted gives a clear indication that the transformer operates properly until next scheduled outage. The primary test performed by the Delta 4000 is AC insulation integrity and is completed by measuring the tan delta, also known as insulation power factor. Transformers are divided into 2 major categories of construction and therefore into 2 types of testing, mechanical and insulation. Today's focus will be on transformer insulation, as we see this as the main determinant to the aging of transformers. For a typical 2-winding transformer, we are interested in 3 key insulation measurements: high winding to low winding, high winding to ground, low winding to ground. Some newcomers to this test assume we test between phases, but it is between windings where test is conducted, as well as winding to ground. Preparations and connections. Remove all connections to the transformer bushings, including lightning arresters and bus bar. Isolate neutral winding from ground connections. We prepare the Delta 4000 by connections to transformer ground. Short all phases for each winding together, ensuring shorting leads do not droop. Connect HV and low voltage red lead to windings. Transformer is now ready for testing. We are now required to fill in nameplate information on our 2-winding transformer form. This includes critical information such as oil temperature, required to evaluate test results. Next, we check off our overall test. We ensure that the proper test voltages are set for both high side and low side testing. Once properly set, we depress the test button and test sequence will begin. Once interlocks are depressed, voltage is applied to winding and tests are executed. We can now observe testing as it is automatically completed, noting any unexpected results. We review the results and determine if they are acceptable. We are now ready to test the low voltage portion of the transformer. We exchange the high voltage lead and low voltage red lead on top of the transformer. Ensuring that the proper test voltage is selected for the low side, we now depress the test button, which begins the second series of tests. Once prompted, we close interlocks at appropriate time, and test voltage is once again applied to transformer. We can observe the results as they are completed on the dialog box. Once we see the results are as expected, we can confirm good insulation condition of the main body of the transformer. For proper correction of results, we must input correct transformer oil temperature into nameplate info. Temperature can change results significantly, and so correct temperature is critical. Temperature correction graphs place all transformers and bushings into 1 or 2 categories, which is not accurate for many of our critical assets. As can be seen by this sample of actual temperature correction for various transformers, results can vary significantly. With the Megger Delta 4000 and its patented intelligent temperature correction feature, we are now confident that the results are true at any temperature we test at. With our busy lives, we seek to do more within our day, and the importance of keeping the lights on is critical. In today's world, power outages are considered significant events, which are reported and measured as a society's quality of life.
Megger has been a pioneer of electrical insulation testing since 1885, and today offers one of the broadest portfolios for testing transformers. Commissioning tests and repeated preventive maintenance checks are crucial and often seen as a prerequisite for the safe and reliable operation of power transformers and substations. The Mega Transformer Test Van is a state-of-the-art integrated measurement system for the on-site condition assessment of power transformers. The biggest advantage of the Transformer Test Van solution compared to separate or multifunctional instruments is its immediate readiness to test. All leads are on reels, pre-connected to the test instruments. Software-controlled switching eliminates the need to climb the transformer several times. This results in increased productivity, safety, and user comfort, not to mention the air-conditioned, office-like working environment of the van itself. The rear compartment is separated from the operator compartment by a transparent partition and contains all the necessary cable reels to connect to the test object. The user-friendly connection diagram is immediately visible, placed inside the door to facilitate the setup of cables and leads on the test object. Roll out the respective cables. Attach them to the transformer bushings and plug the cable ends into the output panel of the switch box. All instruments are mounted on racks under the table and, if required, can be easily removed for standalone use with their own accessories. In the core system, 4 applications are integrated. Additional applications are also available. A central touchscreen computer running PowerDB database software can control the instruments and collect the results. The user can select and prepare test circuits through the control unit and continuously monitor all safety-relevant parameters. Insulation tests can identify the deterioration of electrical insulation. High-voltage AC tests measure the dissipation or power factor and capacitance of transformer windings and bushings. Insulation resistance is determined between windings and tank using a high-voltage DC source. Turns ratio and winding resistance are low-voltage tests performed on every winding individually. Usually, they are done to assess the condition of windings, contact points, and the proper operation of tap changers. Winding resistance and ratio measurements should be performed in all tap positions. Remote control of the on-load tap changer simplifies the test routine. Certain tests are sensitive to core magnetization, so demagnetization should be performed after measuring the winding resistance and before returning it to service. An optional power generator, driven by the van's engine, can provide enough energy to complete all tests autonomously. After test completion, finally disconnect the test leads and roll them back onto the reels. The transformer test van concept combines routine electrical tests and advanced diagnostic techniques to facilitate a complete transformer check in field. Testing with the transformer test van saves substantial amounts of time and helps prevent accidents.
Good morning, everyone. My name is Ken Petroff. I am the Power Transformer Product Manager out of Megger Valley Forge. I am here today to present to you the benefits of 1 Hertz power factor testing for insulation condition assessment. We will be touching on a few of the videos that we were just watching during that brief intermission, and how they can all be related together to improve the installation condition assessment for your transformers, for your bushings, really any asset that you need to perform AC insulation testing on. But before we get into the 1 Hertz discussion, we really want to take a step back and see where we are today with the state of line frequency power factor testing. The line frequency power factor testing is performed at 50 or 60 Hertz, depending where you're at in the world. And what you want to do after you obtain those results is to correct those results back down to 20 degrees C. And the way that most people do that today is using temperature correction tables. You've heard the discussion, and especially in those videos, about ITC, the individual temperature correction, and the importance of using that instead of tables. Because if you read through the standards, there's even some notes in there that says that no single correction curve will fit for all cases. So the correction curves are very good for brand new assets that are in ideal condition. But as soon as that asset gets put to work out in the field, if it was manufactured in the UK, but then installed in Sweden or installed in Saudi Arabia, they are going to age differently. So using the temperature correction table is not going to be appropriate for each one of those assets. You need to evaluate it based on its unique aging and deterioration that it's undergoing. So as a side to the 1 Hertz, we will also be looking at a bit of ITC, or individual temperature correction, today. But once you've corrected those values, then you are going to want to evaluate those results by the limits set in the standards. Unfortunately, there is quite a bit of doubt when the readings are not as expected, and you can improve your analysis with a little bit of trending. And here we see a graph from 1969 through 2017 that shows the high to low power factor measurements for a certain transformer. And we can see that the values change a little bit over time, but small power factor or dissipation factor changes are not conclusive. And this is where we are looking at 1 Hertz to help improve our analysis. And if you hear me talking about power factor, dissipation factor, they're all the same terms that you can use for measuring tan delta, and I just tend to use them interchangeably. So please don't let that cause any confusion. But at the end of the day, when we look at the 20C measurements at line frequency, what we notice is that early deterioration is not noticeable. You can notice when something has degraded quite significantly, but by that time, it's often too late for the transformer, or asset or bushing. So we want to do what we can to evaluate that asset sooner, and that's what we can do with 1 Hertz. So why are we focusing specifically on 1 Hertz? Well, when you do line frequency power factor measurements, you have to take the transformer out of service. You have to short the high side windings together, the low side windings together, as we saw with discussions about the IDACs. And with the Delta 4000 and with 1 Hertz testing, what we are able to do is use that same test connection that you're already using for your line frequency power factor test. And with just 1 minute of additional test time that doesn't require any additional configuration from the software, we can look at the 1 Hertz values to validate expected line frequency results. We can then confirm questionable line frequency measurements. And perhaps most importantly, we can detect problems within insulation when line frequency looks acceptable. And what I have prepared for you all today is a look at a handful of select case studies that we've put together over the past year to highlight exactly how 1 Hertz is going to help you achieve these 3 different goals of validating, confirming, and detecting problems. So why does 1 Hertz provide a different type of analysis rather than line frequency? If we look, let's say, at a transformer, it's made up of spacers, it's made up of barriers, and it's also got some oil in there. And when you apply a certain frequency, the response from these three different X and Y components will change. So if we look at line frequency, when we apply that, we see that we get a relatively uniform response from the transformer. And if we change that frequency, say down to 5 millihertz, you can see that now the response from the transformer or the asset will be localized into one area of that XY diagram. So it gives us the ability to look at specific areas, and that ability helps us determine more about the asset than what we can right at line frequency. So the first case study that we're going to look at today is using 1 Hertz to validate expected line frequency results. And here we have a 1965 transformer, 56 MVA, that was tested at 19 degrees C. Again, temperature is very important to note when you're performing line frequency measurements. When you're performing power factor or tan delta measurements, because you must take it back to 20 degrees C in order to properly evaluate. So here, looking at this transformer, we measured high to low, high to ground. This is a auto transformer, so we're measuring high and low together and measuring to tertiary, and vice versa, applying high voltage to tertiary and then measuring to high and low. And we can see, looking at the values here that we measured, and also looking at what was corrected just using the temperature correction tables, everything looks in line with what you would expect for not only a service age transformer, but a new transformer as well. All the values are looking very, very good. If we then look at 1 Hertz, we can see that the values are quite in line with what we measured at line frequency. And if we take it one step further, we then look at the ITC, or the individual temperature correction. The values from line frequency did not change significantly, but you see here now we can provide an analysis for this transformer at 1 Hertz. It's important to note that these standards only provide temperature correction tables for correcting values at line frequency. There is no standard today that exists that tells you how to correct any frequency other than 50 or 60 Hertz. The only way to correct 1 Hertz or 10 Hertz or 15 Hertz is to use individual temperature correction. So as we go through these case studies, you'll see that if we're looking at temperature correction tables, we only show values as measured, and then we need the ITC to provide that correction back to 20 degrees C in order to get the evaluation. But here on this service age transformer, everything is looking pretty good. But with the Delta or with the TRAX plus TDX, we do not provide insulation assessment. We are only providing you with additional information on which transformer or which asset should be tested further. And in order to get that proper insulation assessment, you're going to need to perform the DFR results that you can do with the IDAX. And when we do that on this 1965 56 MVA transformer, we can see that, even though it is more than 50 years old, the moisture contained within the asset, it looks quite dry, and the oil conductivity is looking very good as well. So with this, what we can say is that the 1 Hertz validates expected line frequency measurements results. So the line frequency results came in, less than 0.5% tan delta, and the 1 Hertz was also showing low values, meaning that the transformer is in a good state, and we can trust that those line frequency measurements that we got were good. And then lastly, the DFR is required to understand the exact insulation condition. The Delta 4000 and TRAX plus TDX are only telling you a little bit more information about where you may want to look. So if I were to end my presentation here, a lot of you would be saying, so what? This doesn't really help me in what I'm doing today. So going into the other case studies, what we will look now is using 1 Hertz to confirm questionable line frequency results. Here we are going to look at the bushings of a transformer measured at 10 degrees C. Looking at the high side bushings here, we see that the H2 bushing is a little bit higher than its sister bushings, H1 and H3. But I think I speak for a lot of you in the field. If you were doing this testing, you would not raise any alarms because this particular bushing is 0.06 deviation from nameplate. A lot of you would think, yes, everything looks good. This transformer, this bushing can be put back into service without any further action needed. But because you're able to get 1 Hertz with the Delta 4000, we perform that automatically, again, using the same test connection and only 1 minute of additional test time. And what we can see when we use temperature correction tables and just looking at the measured values, that the 1 Hertz value for H2 is significantly different from its sister bushings. So this confirms this higher or elevated line frequency power factor measurement that we saw earlier. But again, we need to then apply individual temperature correction to this result in order to provide an assessment. So if we do that, we can see that the line frequency result now, instead of being 0.06, it's 0.16 from nameplate. So a larger deviation than what we saw using the inaccurate temperature correction tables. And looking at 1 Hertz, now we see that there is quite an extreme difference compared to its sister bushings of almost 15 times. So now this is really showing that this H2 bushing, there is something different, something has changed. We know that sister bushings are typically made by the same manufacturer, made in the same year for the same rating. So they should all age the same. When they do not, then we can start seeing changes, especially down at 1 Hertz, where it's more conclusive, more informative than line frequency. Again, these changes or these differences at line frequency results up to today, I think a lot of you would say that there is not enough information here to make a determination that something is wrong or that we need to do something with this bushing or this transformer. But again, since the Delta just tells you where to look to improve your maintenance test plan, you do need to bring out that IDAX with the full DFR to get the definitive answer about this asset. And when we do that, we can see that the moisture on a select bushing that was looking good, in this case H1, is down at 0.7, so it's looking very good. But the moisture for H2 is up at 2.8% at moderately wet. So we know that there is something wrong with this bushing looking at 1 Hertz, and then IDAX DFR tells us exactly what is going on. So the conclusions at the end of testing this 1965 transformer with 135 kV bushings at 10 degrees C, we see that 1 Hertz can confirm early and advanced degradation of insulation. In the first case study, we saw that 1 Hertz validates good line frequency measurements, and here 1 Hertz is confirming changes to that insulation. With that being said, we are able to improve the lifespan of this transformer because this particular customer can now plan to have this bushing replaced, so that way there is no unplanned outage. We all know that a planned outage is preferred over an unplanned outage. And yes, so using 1 Hertz in this way, again with that same test connection, can improve the maintenance plan that you already have in place today at line frequency power factor. But now we are going to look into a couple of case studies where 1 Hertz will detect problems when line frequency looks acceptable. The first case study here will be looking at a few bushings on a 2002 transformer that was tested at 11.5 degrees C. Here we see the C1 results with temperature correction tables. We see we have some measured values here. Everything is pretty close to one another. And then when we correct back to 20 degrees C, everything looks good. And I would challenge anybody out there to tell me, which bushing has the problem, or more so, I would say, which bushing is showing a deviation in results that you would feel confident to take to your manager or your supervisor and say, hey, we have a problem with this particular bushing and we need to take action. Looking at just line frequency tan delta, there is not enough in there that is going to be convincing to anybody. So we need to take it one step further and look at the 1 Hertz value. And when we do that, we can see that the X3 bushing is showing a large deviation again from its sister bushings. Once more, with temperature correction tables, it assumes a certain state, and we cannot use the temperature correction table to accurately correct line frequency power factor, and it is not applicable to any frequency other than 50 and 60 Hertz. So we must look at the ITC values. Looking at the ITC correction for this particular bushing, we can see that now it has changed by 0.14% power factor, and according to the standards, if the power factor for a bushing increases by more than 50% versus nameplate, then that is a reason for investigation. So even using ITC in this case, the line frequency tan delta would tell you that there is an issue that needs to be investigated. But with 1 Hertz, we're able to further confirm this problem. That deviation is even more extreme, 11 times different. So what can we say about 1 Hertz in this case? Number one, that service-aged insulation can appear within limits when you are using temperature correction tables. The temperature correction tables do not take into account the unique aging and deterioration of an asset. That can be your transformer or your bushing. So you must look to a different way of correcting that value other than the tables. The way that you can do that easily is to use a test set that can test at frequencies other than line frequency, all the way down to 1 Hertz, to provide you with that additional information. So that way you can detect this early and advanced degradation of insulation. And again, you can use this to improve your maintenance strategy, because if you just looked at line frequency for this particular transformer, you may not have taken any action. You can say, oh, yep, we're going to test it in 7 years, and we will see what we get at that time. Unfortunately, waiting that long in this particular case may result in an unplanned outage. So you can either decide to come back in another 6 months to retest again, or you can choose to replace this bushing. However, let's say that you did not have this particular bushing in stock and you needed to order it from the manufacturer. Well, again, you've improved your maintenance strategy, because now you can plan for the future in ways that you were not able to before. And once again, with the Delta 4000, with this 1 Hertz measurement, we cannot tell you exactly what is wrong with that particular asset. We can only tell you where you should focus your energy. And if you want to get the conclusive analysis, you must bring out that IDAX DFR to figure out, is it a problem with moisture? Is it a problem with conductivity? So on and so forth. And the last case study we'll be looking at today is the commissioning test that was done on a 2019 16 MVA transformer that was tested at 25 degrees C. Once again, we start out looking at the line frequency power factor measurements. And in this particular case, they look excellent for a new transformer. Everything is well below 0.3, just a great looking transformer overall. However, when we look at 1 Hertz, we start to see some elevated values. And if you remember back to the first case study, the line frequency and the 1 Hertz values were pretty close to one another. But here we're starting to see this large deviation. So we can see that the values are trending upwards. But once again, this is only temperature correction tables, and we must look at the ITC in order to get a proper evaluation at frequencies other than line frequency. Looking at the ITC correction for 1 Hertz for high to low, we can see that the insulation for this transformer is being rated as aged. However, as I mentioned, this was a commissioning test that was being done on this transformer. So why would a brand new transformer that has never been in service show aged insulation? There must be something wrong with this transformer. So again, we're using this 1 Hertz to improve your maintenance and commissioning strategy. When we bring out the IDAX DFR, we can see that this transformer, while it is still dry, and it is showing some elevated moisture and some elevated oil conductivity when we would expect these values to be quite a bit lower for a new asset. And as we know, the more moisture you have in an asset, it will significantly reduce the overall lifespan of your transformer. So the Delta 4000 pointed us to look at this DFR test, and this 1.6% moisture being high along with the oil conductivity means that if this transformer was put back into service with no further actions, it would automatically lose a certain percentage of life rather than if its moisture was low. Unfortunately for this particular customer, when this test technician brought this to his management team, they noted that there is no moisture limit for transformers less than 150 kV. But this technician, knowing this information about moisture on a transformer and its overall impact on lifespan, wanted to find a way to force his company to take further action to improve the asset lifespan. And what he knows is that there is a limit for moisture and oil for any type of transformer that they have. So what they did was they took 2 separate oil samples, extracted them at 26 degrees C. They took those to the lab, and what they found was that the moisture was at 15 and 16 for each one of those samples. So in the end, he was able to fail the commissioning on this transformer because of this high moisture and oil. And if you look back at the IDAX DFR results, it had already confirmed that. But since there was no moisture limit for the overall transformer for this size, the user had to get creative and find a different way to fail this transformer. But in the end, it goes and it confirms that the use of 1 Hertz is effective for commissioning, and it can show problems with an asset before it goes into service. As I've said multiple times, DFR is the definitive method to determine insulation condition. And for new transformers, you really want to have the moisture and the oil conductivity as low as possible to have the best possible lifespan. So overall conclusions, what can we say here? First of all, the line frequency power factor assessment is insensitive to developing changes in insulation. We saw when line frequency looks good, when line frequency looks questionable, and then finally when line frequency looked good, but it was actually the insulation condition was not good at all. The temperature correction tables do not take into consideration the unique operation or aging of an asset, and therefore are inaccurate. And finally, it's only applicable to line frequency power factor. So if you are doing measurements at frequencies other than 50 or 60 hertz, let's say at 1, 10, or 15 hertz, you must use a different method to correct that down to 20 degrees C, and that will be individual temperature correction. Trending line frequency power factor at 20 degrees C, while it does help improve your understanding of changes, when changes happen, oftentimes they're not conclusive. And how many people today can say that they have a full history of their line frequency power factor results? Most people cannot. So trending over time, it's not always available, and there must be another method. And finally, why would you want to draw your conclusions from results that were corrected using incorrect or inaccurate temperature correction tables? Finally, some people may compare their line frequency power factor results to a proprietary database, but those often come with high membership costs. They're not readily available, and like the two mentions previous to this, those results are corrected to 20 degrees C using inaccurate temperature correction tables. So not a whole lot of use there. But for 1 hertz, we can say that using the same connection as line frequency power factor test and 1 minute of additional test time that is automatically included with line frequency power factor testing without any additional configuration can provide an immediate assessment at any temperature for your asset without the need for trending, without the need for comparing to a proprietary database. You get information on the spot that tells you where you should focus your maintenance activities next. And that lets you know that, hey, my line frequency power factor is good, no further action is required. Yes, my line frequency was looking bad, and I can confirm that with 1 hertz, but perhaps most importantly, using 1 hertz to detect problems where line frequency looks good and is deceiving. But overall, we know that you're going to continue to do your 10 kV line frequency power factor testing today. We are aware that there is a drive in the industry to do less and less testing, and you are not going to go away from the standards. So, of course, do your high voltage line frequency power factor test, correct down to 20 degrees C. We recommend using ITC. But then if you are going to be doing this test, you are going to be taking the transformer out of service, connecting up a test set. You should really use a test set that provides this 1 hertz information. That's that 250 volt 1 hertz corrected down to 20 degrees C. Because if not, you are going to be missing out on valuable information that you can use to improve your maintenance test strategy. And then finally, if you want to know exactly where the problem is within the asset, you are going to need to bring out that IDAX with the DFR to tell right where the problems are. And that brings me to the conclusion of my presentation today, and I look forward to answering some of your questions now.
Thanks, Ken. There's no questions have come in so far. Just there's one just come in actually. Can you test at high voltage with 1 hertz?
So with the Delta 4000, we have a limitation of 250 volts. But if you want to test at high voltage, you can use the IDAX with the VAX, or the new IDAX that came out recently. I believe that goes up above 1 kV. So yes, it is possible to test at voltages higher than 250 volts. But this is typically only required when you have a specimen with low capacitance. So if you are testing bushings, it may be required to go up to a higher voltage. But if you're testing overall in transformer, it's probably not going to be required.
Great, thanks, Ken. And is there a noise problem at 1 Hertz?
So there is not a noise problem since we are measuring at a frequency other than line frequency of 50 or 60 Hertz. There is no noise problems when it comes to that. The signal tends to be a little bit smaller as part of the overall what we are applying. But the Delta 4000, the Trax Plus TDX, the IDAX, those are all very, very sensitive pieces of equipment. And we have seen no issues testing in large transmission substations with obtaining these results.
Great, thanks, Ken. That concludes the questions. So thank you very much. And I will now hand over to Lutz.
Good. Can you hear me?
We can hear you, but we can't see you, Lutz. If you're able to turn your webcam on.
Yeah, maybe
that's great. Perfect.
Thank you. Okay, good. Can you see my presentation also? No.
Yeah, absolutely. Yeah.
Okay, perfect. Good. Hello from my side. My name is Lutz Hulke. I'm most times responsible for the German speaking countries and responsible for transformer testing. I'm as application expert, and also new for me also as for the whole company, I'm responsible for the partial discharge stuff. When I say it's new, I would like to show you a bit about that. It's now 2 years ago that we that Power Diagnostics became part of Megger, and Power Diagnostics is located in Aachen. Aachen is somewhere in Germany, but it's a border to Netherlands and Belgium. So there we have now another factory that is dealing mainly with partial discharge equipment. And that is really great for us as Megger, as this fills a gap in our product range. And they offer products not only for offline diagnosis, but also for online diagnosis, and this mainly therefore monitoring solutions. I give you just a brief overview just to show you how this gap is filling out here. We have seen this table already from Sigrid TB445, transformer maintenance, and this table shows that we as Megger have a wide range of transformer products or products for testing transformers, and for the different tests we offer the different products, and especially for the partial discharge stuff we were lacking so far, and since 2 years now we have the possibility to offer you solutions for PD electrical, PD UHF, and PD acoustics. Okay, now coming to the topic. The topic will be PD monitoring on power transformers, and here's brief the agenda for this presentation. So starting with the motivation why we should do this monitoring, why we should do the do things, and of course some root causes and theory about partial discharges. Then we will continue with standards and definitions, and then at the end I will show you the technical implementations for offline as well as for online, and that means monitoring solutions. Yeah, the motivation, of course, PD monitoring and testing of power transformers, where there is an increased population of aged substation equipment worldwide. That is what we see around the world. In the past, no extended transformer maintenance programs took place. This is not the case for all regions, but for some this is definitely the case. Especially for those where there not so many outage times have been, there is, they say, no need for specific maintenance of static grid assets. Delayed or cancelled investments by deregulations and uncertainty on the condition of numerous transformers. This is definitely one point where we see this demand is coming from. Next point, possible consequences: an increased failure rate and risk, unexpected outages, long downtimes, associated safety and environmental risks, and tremendous repair and transportation costs. And transformer maintenance today looks like this, that you have different asset management approaches depending on who you are and where you have your asset. New maintenance strategies like predictive maintenance. You want to have cost and time saving solutions, and of course, priority is the condition assessment. Taking a deeper look into the transformer itself, what is here the driving force? If we look into a transformer, the main failures are in the insulation. This is what comes from several presentations or from publications. Also, we have found problems in the bushings and windings, and these things in the insulation, bushings and winding can be detected via PD monitoring. Also, another statistic says this: if we go to the CGRID TB642 for transformer reliability survey, we find that the dielectric and is the main problem for those transformers, that they fail, and these early phase, and this can be detected with this partial discharge measurements. If we take a look at these bath tube curve, you see on the bottom, you can find that we have in the early stage of a lifetime of a transformer, we have an increased number of failures, and in the end of lifetime, we have an increased failure rate on our asset. This is a normal curve that you find for almost all assets, and this means you have this early stage. You should take a closer look when this comes to improper FAT, transportation, or on-site commissioning. And then in the middle, of course, it can happen some random failures caused by special stress like high load or lightning or whatever. And at the end of the day, or end of the lifetime, as I said, we have failures due to aging of our insulation materials. And it would be good to have also here a closer look to our transformer. Now, what are driving forces for different people? If I'm now a utility or operator, I would have the following interest: reduce of life cycle cost, definitely, mitigation risk of downtime or blackout, increase of availability and operation time, cost reduction due to change from time-based maintenance to condition-based maintenance, reduction of reinsurance fees, post-failure event obligations, less redundancy in the grid, no spares, unpredictable load and system stress due to renewable energy feed-in, and a long lead time for replacements. This is the driving forces for utilities. On the other hand, we have, of course, the manufacturers, OEMs, and for them, the driving forces are demonstrate the highest quality and long-term insulation system stability. We have these, it's possible to extend the warranty if you take a look at the condition of your asset, mitigate risk of failures during warranty, remote support and diagnostics, added feature value for the asset, service and maintenance contracts, offering an all-in-one solution from the factory till the end of life of a transformer. So these are the driving forces, the motivation for doing this PD monitoring. Next topic would be what are the root causes and the theory about partial discharges. If we take a look into a transformer, we see that there are different ways that we can find those partial discharges. In this photo, you can see they have some surface discharges due to low quality paper insulation. This is black stuff here. We can also see that here in this case, it is due to tertiary winding, something that PD patterns discharges from an in-tight cable connection. So these are different failures you find in transformers, like inferior quality of the insulation materials, fundamental design related to problems, incomplete or improper processing, assembling related problems. Of course, humidity in oil causes PDs, and the aging of our paper insulation can cause partial discharges in transformers. Also in the bushings, we see that there are partial discharges occurring, inferior quality of insulation material, fundamental design related problems, as we see often at the resin bonded paper bushings, incomplete or improper processing, and assembling related problems can be detected with partial discharge measurements. Most common root causes are inadequate vacuum stage prior to impregnation, so there is still something in our transformer before we fill it. It means also insufficient drying of the active part before oil impregnation. This can all lead to partial discharge. Further stuff can be remaining conductive particles in the oil, or then you have a free particle within your tank, and this can lead to partial discharges while the high voltage is on our transformer. Increased water content in the oil, that means also reduced breakdown strength. Missing electrical connections, this can be detected. Poor contacting of tap leads towards OLTC, and drops of casing glue in areas where elevated electrical fields strength is. So what is now the impact of those discharge on transformer insulation, including its components like bushings and tap changers? So the severity depends on the nature of the partial discharge and location in the main tank. Accelerated degradation of insulation materials, gases due to strong PD activity causing subsequent deterioration mechanism. This is mainly for ozone production, and this, of course, you mainly find if you're in connection to air, so mainly dry type transformers. Overheating due to hot spots, high energy PD weakening the whole system, reduced life expectancy of the transformer, and worst case scenario is the unexpected breakdown. Okay, now a few words about a PD itself. So the PD theory. The partial discharge is a breakdown of a small area of the overall insulation. So it's not a whole breakdown, so the insulation does not fail, but it is a small part within our insulation where this discharge happens. So each of these PD pulses generates different measurable electrical signals, and this can be is first of all a local displacement current pulse, what is inside the in this small part where the discharge happens over the insulation. And then we have an electromagnetic pulse as we have this discharge, and this can also be an acoustic signal as if we have a pressure wave somewhere. So these local displacement current translate into a voltage pulse over the measurement terminals due to the RLC network of the transformer. The rise time of this original pulse is in the range of 1 nanosecond, and this can be translated into a bandwidth of 350 megahertz. Nevertheless, with our RLC network of our transformer, this means we have a lot of attenuation inside and dispersion, reflections and filtering. That means that we can only measure a signal up to 20 megahertz at the test tap where we normally do this decoupling of our signal. So the signal stays up to some limitation, is correlation with the real discharge value. This is a good thing. This means according to IEC 6270, with the no imprecisions for failures within the winding, so it's up to 50%. If we go now to the different ways how to display such a partial discharge, there are a few ways how to do that. The simple meter display we find on almost all our instruments, that you just see how many picocoulombs are there. Then you have the possibility to synchronize this with the voltage, and then you can see on the one hand the how many pulses or how high the pulses are and at what time they occur with respect to the voltage applied. And then we have the phase resolved PD pattern, and here you see not only the height of the partial discharge, but also how many are there, and this is given by the color. So another point I would like to say, because this will it's always asked, what is now the UHF method? So the UHF is the only different way how to measure or how to detect the partial discharge inside your transformer. This partial discharge creates an electron avalanche, and this causes an electromagnetic pulse which is radiated in all directions from its origin. So as mentioned, these discharges in oil or solid materials can show frequency components even above 350 megahertz. And those UHF pulse signals can be decoupled by UHF antennas. What you need to have is now a UHF antenna. And this is what we see in a few slides later. So these UHF signals cannot be correlated with the amount of discharge at its origin. So there is right now no calibration in terms of PC applicable. Nevertheless, there are some standards that try to make some comparison and give some recommendations how to deal with that topic. The UHF signal strength strongly depends on location of antenna and travel paths over the electromagnetic pulse. Third way to see our partial discharge is the acoustic stuff. So if we have somewhere a discharge, this causes also some acoustic signal, and this is caused by the electron avalanche, causing a pressure increase with impact to the surrounding materials. So this is a bit slower as it transfers on faster longitudinal signal components. The signal spectra is in a range of some megahertz at its origin, and the signal strength measured with piezo sensors from the transformer tank strongly depends on the travel paths and materials involved. So the acoustic signals strength can be correlated with the amount of discharge, and the acoustic signal is typically used for location of PD courses only. Now, if we compare these three signals, we see it here on this slide. First of all, on the left-hand side, you see this typical electrical PD pulse taken from a test tap of a bushing. The photo in the middle shows you UHF PD pulse with much higher frequency, and you see these pulse packages more or less. And on the right-hand side, you see three signals from acoustic measurement. So you have three antennas there where we measure the acoustic signal. Summing up this theory, I would like to give an overview about the physical effects of the partial discharge. This is taken from the TB676. The partial discharge itself emits different things like optical effects. So if there is a possibility to watch, to look into the transformer, it could also be seen as a light. We see that it's a heating there. Then we also what is happening with partial discharge is a pressure wave, and this means some sound, and then we can use these acoustic sensors again to detect this. We have chemical effects. We have a high frequency wave, and we have the typical electrical signal that we can measure. So we have two basic kind of detections. This is the electrical way to detect it and the non-electrical methods. The non-electrical methods are the acoustic, chemical, and optical. So all related to the blue arrow, and related to the red arrow, the electrical things like the, and there we have the conventional measurement method described in the IC 6270, which means narrowband, limited bandwidth, limited wideband or wideband measurement. And then we have the high frequency measurement technique and the UHF, the ultra high frequency measurement technique. Coming now to the different standards and definitions we have about this topic. Power distribution transformers are a vital part of every distribution network. These transformers are complex structures of mixed materials and components. And what typically starts in the lifetime of the transformer is an extensive factory acceptance test and the requirements there. So this is the FAT, what we have at the beginning. Numerous standards address exactly this factory acceptance testing of power transformers, as well as distribution transformers, as oil-filled and dry-type transformers. So there, for the different transformer types, we have enough standards to do these factory acceptance tests and the type tests. Here's a list for those tests, starting with the IEC 60-70. This is the horizontal standard for the PD measurement, and the IEC 60 or 60. This means this is the horizontal standard for all HV measurements. And if we then go to the transformer standards, it's in our European world, the IEC world, it's the 6076-3 and -11-3 for power transformer and -11 for the dry type transformers. The 61378 is for HV transformers. So this is HVDC transformers for the new applications there. Additionally, we have the IEEE standards, which we'll handle in C57.12. And there are the different standards for the different transformers, like dry type, oil immersed, and all these things can be found there. Maybe I should give a rough overview about what possibilities do we have on site, because this is also already mentioned by Joachim this morning. So we have a problem there. If we take a closer look what we want to do, what we want to test out if we are on site. As mentioned, all the standards that have been shown on the slide before are mainly made for routine and type testing. So you have normally a shielded high voltage laboratory and everything is fine. You have your test field, and you're it's a factory or it's a repair shop, and can do the tests according to the different standards with variable, tunable, high voltage, mainly from motor generator test set, with step-up transformers, inverter controlled systems, or others. So this is how you normally have it in your for your factory acceptance test and in your laboratory. But if we go on site, we do not have any standards. We have some. That's a good thing. We have at the moment already a few recommendations by IEEE and by Secret. These are the guides where you find recommendations on how to do these tests and on what levels you should perform these tests. And this, if we are on site, we can distinguish between three main parts. One part is this on-site offline testing. This means that you try to make the factory acceptance test again on site. So you need to bring somehow a voltage source with you that you can test at different voltages or elevated voltage your transformer. If we go now to on-site online measurements, we use the grid, or the voltage is coming from the grid, and then we can just measure with this voltage our transformer. We need to place our sensors, and then we can do these measurements there. And if we take a next step, we can do this continuously, and we call this monitoring. So this is the on-site online monitoring. What we do there is that we have our sensors and our measurement systems connected to the transformer the whole time, and it measuring the whole time, and then we get some values there. So this is the on-site online monitoring. So again, the different measurement types, just for the different objectives, I would like to distinguish it that way. Type and routine tests is the FAT. This test you normally do for quality control to find PD activity at an early stage, pass-fail criteria according to predefined PD acceptance levels, and PD due to design, processing, assembly, materials, or any other root cause occurring at manufacturer site. Then we have the on-site offline PD testing. Here, this is mainly done for quality check to find PD activity ahead of energizing of the transformer. So for commissioning or recommissioning, so PD might be caused by transportation, assembly, or processing mistakes, or other root causes during commissioning or recommissioning after repair. Then we have these on-site online PD measurements, so it's a kind of temporary monitoring. This means temporary, typically time-scheduled or condition-based measurement to take a snapshot of the insulation condition to find severe problems causing high PD levels. The main benefit compared to on-site offline PD testing is that you don't have to bring your high voltage source with you. The disadvantage is that you have to test at grid voltage. And finally, this is marked yellow as this is the main topic for this presentation, is the online PD monitoring. Here is the continuous 24/7 monitoring and unveils incipient, changing, or emittent PD activity at an early stage. You see if they change something, you will see it, you will get it. In context of special load conditions and with further comparable measures such as DGA, the capacitance, ton delta measurements, temperatures, and load, this can be all correlated, and then you may find at a very early stage if there's some problems in your transformer. Coming now to the technical implementation of our different systems, I would like to start with the general, or where it all starts, is with the IEC 60 to 70 compliant measurement. So the normal compliant measurements, what you do there. This is the typical test setup you have. You have somewhere a high voltage generator. You have your device under test. In this case, it is a transformer. You have a coupling capacitor. You have a quadrupole. This is typically built inside this or on the bottom of those coupling capacitors. And then you have a PD detector. This can be an ICM compact, or for transformers, you better use an ICM system, would have maybe more channels in parallel. For these IEC 60 to 70 compliant measurements, you need to do a calibration in advance of the measurement to know what is the actual value of the coulombs that you measure during your measurement. And therefore, this must be placed over the devices under test, close to the other connections. If we now take a look, how does it look like on a factory acceptance test on a transformer? So we have a transformer with 3 bushings, for example, and there you see at the bottom of the bushing are these test tabs, and exactly at these test tabs we will connect our sensors and our 3 amplifiers, and with a signal we will go to the test room, and there we will connect it to our test instrument. So this is at the test tab itself, it looks like this, that you connect the test tab there, then you have the quadrupole and then the resistor amplifier, sorry. If you're going to transformers that don't have test tabs on the bushings, typically below 70 kV, then of course you have the possibility to decouple these PD signals with normal coupling capacitors, as we do with all other test units devices, like for rotating machines or instrument transformers. Besides the coupling capacitors with inbuilt quadrupole, we have directly the preamplifier, the RPR1, and then we go to the ICM system to have in parallel the 4 measurement channels, and then the acquisition board with the computer. There are additional methods of decoupling for the diagnostic PD testing. Of course, it can be done with high frequency current transformers. You can find in this picture here. So it is in clap on a ferrite where you have these HFCTs, and you can get the partial discharge from this point. As seen in the picture before, various coupling capacitors is how you can get the signal, and this also can be done in strange arrangements, like for example in this case here, where there's the only possibility to get these signals out there. And if we go to further measurement possibilities, we have this UHF method, how to measure UHF pair signals. These are detached like this. They look like this. So you have a long antenna going inside the transformer. Also, this is a UHF sensor that is connected to the wall, or in the window, not in the wall. It's a window there. And then you see it into the transformer. It's a flange sensor. We have the possibility to attach some acoustic sensors. It will look like this, and if they are attached, it can look like this there. And then we have disturbance antennas like this one. If you want to measure any disturbances from corona or whatever, then you see it with those things, and then you can filter it. One remark at this time, as I was describing the offline testing. Of course, offline testing is not only in laboratory on the factory, but also can happen on site. And what we want to do is this factory testing. We bring this factory testing to the site. This is what we try to do there. Of course, with reducing downtimes, active part repairs or coil exchanges, power rating upgrades or oil treatments and regeneration. There's an increasing demand for this on-site high voltage testing, including PD measurements, especially for repairs and component replacements, also for commissioning stages, and for verification of the DGA results and confirmation of Buchholz or PD monitoring alarms. As mentioned earlier, the most difficult thing there is to bring a high voltage source somehow there. It should be lightweight test gear, compact electronic power supplies, typically what is used there. And then, of course, a advanced multi-channel PD detection system, as we know it from the laboratory. Yeah, it depends on how big the transformer is and how high we have to go with the voltage, but then these lightweight high voltage sources can look like this. So this is our container we have there with 38 tons. We have it located in Aachen, and we'll drive around with this in the whole Europe and have its main application for this container testing of power transformers, but also doing some tests of power cables. Good. Now coming to the online stuff, so technical implementation of these PD measurements with our online solutions. You see a photo here of our first implementation of these partial discharge monitoring back to 1998. So we have a real long history already for this kind of measurements. The idea of these online PD monitoring is to assess the insulation health of power transformers and transformer accessories. So PD trending and changing PD patterns indicate incipient failures. The PD pattern analysis assists with failure investigations. So try to find out what is the type of failure, so the root cause analysis. And added value if PD monitoring is combined with, for example, DGA, voltage, tan delta, temperature, and the load monitoring. How to assemble this now? You have seen earlier that we can connect directly to those bushing tab, to these measurement tabs on the bushing. And now we have those fixed adapters here, these BCUs. These BAs, and then we go from this one to the BCU and the multiplexer, and then we from this one, from this BA to the BCU, we can go to the main cabinet where all the information from all the different bushings, measurement tabs come together, and then we they are here recorded, and we do some things like the after processing, pattern storage, trend recording, and giving the warning signals. Additional things can be added, like a DA1, where we can get as an antenna, where we find out what if there is some noise, then we can do the gating here. Also, we can add different sensors, like the UHF sensor or HF sensors, and they are maybe connected into the valve sensor here. The cabinet looks like this here, and the monitoring system itself is a small part here. Coming to the different parts of our monitoring system, we're starting with a bushing adapter. We have for the different bushing out in the world, different types of adapters available. I think it's more than 30 different availables already, but if there are something that's not directly available yet, we will definitely find a solution and maybe make something new. These these are normally made with aluminium enclosure to have it really as in protection class of IP65 for permanent installation. There are surge arresters inside, and the output connector is an N-type. So the temperature range goes from -40 degrees to +90 degrees Celsius. The next unit after these BAs are the bushing coupling units, the BCU, and they collect now this signal that's coming from the BA, and is nothing else like a normal quadrupole. So they make, at the end of the day, on one hand the PD signal, and on the other hand they find out the voltage, where you can just then do the correlation also for the PRPD patterns later on. Of course, this is also has IP65 as protection class, and then high temperature range of -40 to +75 degrees Celsius. Therefore, there's permanent installation. Also, this is in stainless steel housing, available on request. If we go now, talk about these UHF sensors, they are two types. One is that you need to fill in within the flange sensor, the valve sensor, and the other one is the flange sensor. It's decoupled here on those windows. We recommend only for noisy site conditions. Yeah, and you see that you measure a bit different frequency range, but there you can also go and get it into our monitoring system. I'd like to show an example. Here we have you see a cruise liner, and on these cruise liners, there we have, of course, also some electrical network, and those electrical networks are like a small island, and they have a distribution transformer inside, and of course they should be warned if there's something happening with their electricity. So what they do is they installed a lot of capacitive couplers. I mentioned it's distribution transformers, so the watch level is not that high, so there's no measurement tab available. So we added a lot of these capacitive couplers with quadrupoles on top of, on the bottom of them, and superimposed AC voltage signal. So the optimized coupler geometry to fit into the terminal boxes has to be done so that you can also close it again and have a very good installation for monitoring as permanent installation there. What you also should take care is, of course, not only the boxes itself, but the thing between them. So that means you need to have good signal cables for extreme site temperature, maybe, so hot or maybe cold, and also heavy weather conditions. So what we recommend is the high quality PTV Teflon coaxial cable. And what we additionally recommend is to not to go, is a distance of up to 20 meters, not to have it too high. Otherwise, the signal will not be transmitted that good. So additionally, we recommend a CTB2. That means that we have a protective ground in the middle, and that you have these for saving our measurement terminals. As already mentioned, for noise gating, there are different tools available. One is the disturbance antenna, the DA1. So this picks up noise pulses radiated from corona. Other possible options are CTs, so high frequency CTs, the HFCTs. We have the CT1 and the CT100. They pick up disturbance pulses from shields or signal cables or from ground connections. This is how they are normally used. So instrument interrupts PD measurement for the duration of the disturbance pulse, and this is what we call gating. So and now we come to the measurement unit itself. So we have these kind of measurement units, what you place in the cabinet. So this is placed on top here. You have this frequency selective measurement, wideband narrowband filter, spectrum analysis, UHF measurement, dry alarm contacts, and you can also have the IC61850 for your system. This and the other option is the PDMR 500. We go into a stainless steel cabinet with an IC monitor, CTB network interface, iOS main switch built in, and we have the compact design there. If we now go for, if you collected your data and now you want to somehow see it, you want to get informed what is happening on my transformer. So you need to somehow get a mobile communication. This can be done with the PDMON. So we have a cloud server to the instrument at site. This is direct access via virtual IP address, no network cabling, variety of options like VPN, etc. And what you need is a UMTS provider with a local SIM required. Or you do it with the mobile web server, the MWS1. It is operating system independent. We have direct access via local IP address, full description of the API, and access to specified data sets provided by the instruments. As mentioned, it is possible to include this in the 61850 area, so via the hardware interface, and then you get alarming and essential data via this interface. So this is also OS independent, providing of ICDs, full description of all data sets and 6150 relevant documents, and provided data sets such as current readings of NQS, QP, alarm status per channel. Those can be transferred via this IC 61850 protocol. Our software within this system is called ICM Monitor. It is a Windows software. This gives a remote access to multiple monitoring instruments. We have long-term trending and history structure. Also, of course, what you need for monitoring systems is alarm handling. And then if we go to partial discharge measurement, you find in this application also the colored PD pattern acquisition. And you can find it here. And then we have the automated data acquisition, and this connects via USB or LAN directly to your computer. Also, an advanced data management is available. It's called the ICM Expert software. With this database supported handling of all measurements files and supplementary information, you can do stuff like PD pattern comparison or PD pattern classification, and you can do storage of photos, comments, and all instrument setting with each data set. And you can see here the photos, and it's an add-on tool for all our products, not only for the monitoring solution. Maybe you don't want to go for continuous monitoring, but somehow you maybe want to be prepared. And then we have something called temporary online PD measurement. And this means that you already have installed all your sensors, and so your bushing tap sensor is already installed, and the BCU is already installed, and you all bring it back to one cabinet, and then there's no acquisition unit. But you can do this with some kind of temporary monitoring and just connect there while you're still in service. So this can be due to budget constraints or after poor DGA results, no immediate long outage possible, or no fast availability of a mobile test system. How to do this? Yeah, this is what I mentioned. Using permanently installed bushing adapters and BCUs. So this is what you need to have already. Otherwise, you need to turn it off, the computer, the transformer, and then do this installation. Then you have this temporary installation of quadrupole HFCs, HFCTs, and UHF antenna, the PD test equipment, and minor setup modification, installation of corona rings. Notes: these grid systems greater 132 kilovolt generally produces high repetitive external corona. Therefore, we recommend these antennas also, for example. A more limited coverage compared to offline testing, elevated detection bandwidth, and of course, these acoustic PD location attempts are generally more successful with an external power supply. So if you do this acoustic PD measurement, or is mainly done for location, we recommend to do this with an external power supply, not during temporary online PD measurement. But the data interpretation requires an operator with decent knowledge level, but this is, I guess, what is clear for all of our measurements. Yeah, I hope I could give you a brief overview about our capabilities on PD monitorings. Yeah, and hopefully we don't have these transformer failures as you see on these pictures there. This is not only costly, but also dangerous and disastrous. Thank you for your information, for your
Thanks, Lutz. There's a couple of questions coming if you wouldn't mind answering.
Okay.
Can you combine electric, UHF, and acoustic measurements in one system?
Yes. This is can be done, and you can, for example, use the electric system as a trigger also for your acoustic systems there. Yes.
Okay, great. And then just one more. So can we keep the power cable primary and secondary for the PD acoustic testing?
Can we keep the power? Yeah, a good question. So that means you don't want to disconnect the cables. The question is always, what will you measure? What will the failure when you do the measurement? In this case, if you do the acoustic measurement inside, that's what I mentioned. We recommend to do this with an external, with an additional voltage source. So you need to connect this somehow anyway. So yeah, of course it can be done, but always question what will you measure, and yeah, you have to take care. You have to decide that by taking a look at this carefully.
Okay, thanks, Lutz. Just one more that's came in. Can the system give trip of the circuit breaker?
No, not really. It depends on how you do what you do with information. What our system does is it gives warnings and alarms. And what you do now with this information is it depends on the operator itself. I do not recommend to do this directly, because there are so many other things that you have on if there really is a fatal error on a transformer where you need to have a circuit breaker tripping, then you will see it on different other things, not on alarms like for partial discharge.
Okay, great. Thanks, Lutz. So that concludes the questions. So so this is the final roundup of the seminar. So now I'll invite all the speakers to put their cameras on and join us for the panel. And if there are any questions from the audience, please feel free to ask now in the questions tab, and we can deal with them live. Just while they're coming in, I just want to thank everyone for attending. We hope you enjoyed the seminar and found it useful. There is a feedback form that will pop up on your screen as soon as this seminar finishes, so we'd appreciate any comments or feedback. That would be brilliant. And just finally, a reminder that the recording of this entire session will be emailed to you tomorrow, so keep an eye on your inbox for that. So if there's any questions, please feel free to ask now. So I can see one for you, Ola. There's one that's come in regarding your presentation earlier. So can DRM detect contact damages in the OLTC?
So I also seen that he sent me this an email question. And then he added some more information in the secondary email. So basically he wants to know, like, if we detect gases, for example, can we recommend the customer to perform DRM then? So like, first off, like quite often the oil is separated from OLTC. So if I have gases in the OLTC oil, that can indicate, first off, you have more gases there because you have the arcing there. But sometimes you have gases due to heat. So for example, if the timing of the OLTC would be a longer, so you have a longer transition time, and then the transition resistors will be heated for a longer time than they're specified for, that might generate some type of gases. But then you also have this idea of contact cooking, so to say, that you have some sort of coating on the contacts. And there, I mean, the discussion was very clear. So if you test with like a very low test current, you can see those indications. But then the idea is that once you apply the load current, they will not really be there. But I mean, if you see a higher, if the transition resistors contact is cooked, so to say, I guess that also will show up on the transition graph. But if you test with a too low current, you can guess these false, so to say, layers of poor contact that's not really there during the load current. So the short answer is yes, you can use it, but you need to be a bit careful with what test current you select. But I will send you a long explanation in the email and do some references. Thank you.
That's great. Thanks, Ola. Yeah, that's a great point. If there are any questions, and you know they're quite technical, feel free to email any of our presenters, and they will get back to you in their own time if it's quite a technical answer that can't be asked over here. So so yeah, feel free to do that. I'm just checking the questions tab now. There hasn't been any more that have come in so far. So we may leave it there. Oh, sorry, one's just come in. What is the maximum length a PD measurement point can be made from the PD source and still detect the PD?
Yeah, it has been on this one slide. We recommend not to go further than 20 meters. There are, of course, so this means decoupling of the bushing until the PD detector. And then, of course, it's free. Then it's you can have every distance. If it is, if there's bigger distance required, then there are possibilities to do some other things, like maybe have the different acquisitions units and sending the signal, or maybe going for fiber optics. And there are some further possibilities, but we recommend to not go for higher distance than 20 meters, and that is typically not a problem for transformers.
Okay, great, thanks. I think that's pretty much it for the questions. So if there are any more questions, feel free to email our speakers and they will get back to you. Just a final reminder that the whole recording of this session will be sent to you by email tomorrow. So please keep an eye out in your inboxes, and you can watch the entire session or flick to a particular part that you was interested in. So I just want to thank everyone again for attending today, and obviously thank you to our speakers, our experts from Mega around the world. You've been great. So thank you very much, and we hope to see you soon.
Thank you.
Thank you. Bye.
Thank you.